The Zoom controls.
Oh.
The Zoom controls are up there.
Oh, I see. Oh, that makes sense. As long as it's still recording.
No, it'll still screen share that screen.
Okay, screen share.
You're
Screen share.
you're screen sharing that screen, right?
Yeah.
Yeah.
And we can still have presenter notes.
Yeah.
Right?
Are you sure you're screen sharing that screen?
I'm joining and seeing what it's saying.
Sharing the red screen.
Can only do so much, right?
Okay, so let's get started. Good afternoon. Welcome to the first tutorial on human-centered AI for computer vision. So it's so great to be back in person. So thank you all of you for joining us. So for this tutorial, we will have 4 wonderful speakers, including me. We will give you tutorial talks on several topics relevant to human-centered AI. Before I give you an overview of each talk, let me share with you this first. As you may know, so yesterday and today is Juneteenth holiday. So it's a US holiday commemorating the end of slavery in the US. So it's a holiday of special significance in the US South. So we encourage a tendency to learn more about Juneteenth and its historic context and join the city of New Orleans in celebrating the Juneteenth holiday. So it's really a special time visiting the city. So hope you enjoy your stay here. Let's go back to our tutorial. So the topic of this tutorial is human-centered AI. So first of all, what is human-centered AI? So human-centered AI is about reframing the relations between AI and humans. So the conventional thought of AI is algorithmic centered. So as a universe of the research and development, the algorithm is at the center of the universe. So we researchers spend so much time developing new algorithms to improve the numbers on the benchmarks. But human-centered AI provides another perspective. So in this universe, then the center of the universe will be the humans. So we want humans can better enjoy the benefits of AI and we want to better understand and collaborate with AI. So the objectives of human-centered AI is first, we want to have a better understand and collaborate with AI. Also, we want AI can empower humans and augment our capabilities. So let me then first briefly introduce each lecture and talk today. So the first lecture will be given by Professor Judy Hoffman and his PhD student Viraj Prabhu. So Professor Hoffman will talk about responsible computer vision. So she will show you what can we do about it. So she will talk about the measure that we can measure the failure of the models, and also how can we develop better algorithm for higher of computer vision tasks. So the third lecture will be given by Professor Olga Roskovitsky. So she will talk about the fairness in visual recognition. So she will lead us to re-examine the pipeline of how we train the model. So she will provide the insights, how can we adjust the AI design to mitigate the effects such as bias, sort of issues with the AI model. So the last lecture will be given by Dr. Ruth Hong. So she will give you an overview and point you the direction about the recent progress in interpretability. Okay, so without further ado, let's invite our first speaker, Professor Judy Hoffman. So let me briefly introduce Professor Judy Hoffman. So Professor Hoffman is an assistant professor in the School of Interactive Computing at Georgia Tech, and she is a member of Machine Learning Center. So her interests include computer vision, machine learning, domain adaptation, robustness, and fairness. So prior to joining Georgia Tech, Dr. Hoffman was a visiting research scientist at the Preschool AI Research and a postdoc researcher at Stanford University and the
computer vision. This particular lecture is going to be focusing on responsible computer. Some Zoom pop-ups. Okay, so to get started, we can think about some of the ways in which computer vision or machine learning models are used today. And one of the ways I like to think about this is that models are frequently used in a transfer learning setup. What I mean by that is there's an initial phase of. Now, this initial phase might be something as simple as training a supervised model on some large curated data set for some task. We do this all the time. We take an image net, we download weights, and they get passed around. So people do with this. Well, once they have those weights, of course, if you're trying to use that model for exactly the same task, you might use it out of the box. But frequently, what people will do is they'll take this model and they'll make some small modifications. More recently, it could even be self-supervised training. So let's think a little bit about how those initial models are trained. These are going to be reused over and over again by a large portion of the community, both in the academic community and also more broadly. So it's really important that when we think about these canonical models, when we think about the fact that they're going to be used in so many diverse scenarios, we need to have some understanding into when they're going to work. How reliable can they be? Can we communicate this to people so that they can better understand? So of course, we all know that the first phase in a particular data set in mind. So I just mentioned one example where people were using the ImageNet data set. You could use any other data, but this is, as we know, a central part of defining the model. What data are you using? If you want it to be a supervised learning problem, you're going to have to define some label space and get some labels. So if you want to recognize dogs, maybe you'll have to be able to dog.
Sorry to interrupt, but we can also slides, I think.
You can't see slides.
Yep, multiple people.
What?
We cannot see presentation.
Okay, 1 second, we will fix that. Can you see them now?
Yeah, we can see it now. Thanks.
Great. Just, another joy of the hybrid conference experience. But hopefully we have everybody on board now. Okay, so you have these annotations, and now you can go ahead and train this model that you're going to pass along to people. And this has been such a pervasive part of the learning process that, of course, one of the key phases that happens is that we want to collect some large databases that people can reuse over and over again. So for canonical tasks like classification, of course, there's the famous data sets of ImageNet and Places. For detection, you might have generic detection of object categories like COCO, or you might have application-focused data sets, the city-space data set for self-driving. These data sets are kind of collected frequently as a benchmark to be able to start to establish how well a model that might be passed around to other people is going to work. But we have to think a little bit deeper about how these models that are designed, developed, and trained on these data sets are then evaluated. So frequently, the way that a benchmark is going to establish its validation, which is then going to be kind of passed around along with a model in order to specify how well we think a model works, what you'll do is you're going to have a held out portion of this same data set, and you're going to use that in order to measure some aggregate performance metric, like perhaps you're going to measure accuracy when we're talking about ImageNet. So this says that for these particular object categories, you can have an expectation of this particular performance. So for a model that's this large ResNet model from 2017, it was looking like performance was very high. So we now remind ourselves of this transfer learning scenario. Somebody's going to take this model, they're going to think to themselves that I have a performance that's close to 100% on this seemingly complex task of recognizing 1,000 object categories. And you would ideally hope that that is a reliable measure that could be used in your scenario, that you could say that if this model works so well here, it should work for me too. But we know that this isn't really the case. We know that there are limitations to how you can reuse these models in practice. It's of course better to reuse some information, but we have to have some better understanding. We know that these systems are going to be used broadly by lots and lots of people, some of which are maybe experts like those in this room. So if we take this model that was trained on ImageNet, one way in which it can fail is if some of the assumptions about the data change. So ImageNet is a static data set. If you want to apply the model that was trained on ImageNet to recognize things like dogs to the frames of this video, you can't recognize the dog. And really that just has to do with the distribution shift or data set bias between the ImageNet dataset version of dogs and the way that dogs appear in this video. In the ImageNet dataset, we have scraped images of dogs that people have decided to share as still frames. So the types of photos that people want to share of dogs as still frames are going to have a bias towards having the face of the dog visible, a bias towards having the dog in the center of the frame, and have, in general, higher resolution than you might have seen in frames of a video. Now, if we're talking about videos, people don't necessarily take 20 videos and then upload the action, like the dog running. And so instead, the frames of this video, perhaps because of the high frame rate, are going to be lower resolution. You're going to have blur from the subject and the frame, and you're going to have a wider variety of poses than you had in the original still image data set. So all of these changes, though subtle, do lead to degradation in performance of a pre-trained system. If we move on to more complicated tasks beyond classification, think about the task of semantic segmentation in driving scenes. First of all, these data sets tend to be smaller than the still image data sets because it's quite expensive to collect and annotate the frames for these types of applications. And the representation that's needed in order to capture the diversity of the world is much larger. You need to be able to think about all kinds of different cities, all kinds of different weather conditions, and all types of different sensor capture processes. If we try to ask what would happen if you don't have all access to all diversity before you get started and train this initial model, what would be the result? We can imagine thinking about one particular scenario where you're trained primarily on sunny weather conditions and have an underrepresentation of other weather conditions like snow. So your sunny weather, you have a model, it seems to be working really well. You do your benchmark task, you evaluate performance in aggregate across, again, a distribution that's primarily sunny, and it seems to work well. But if we look at a single image from the snowy time, what we find is that this model fails to recognize a lot of the surfaces that have snow on them, like the road and the sidewalks. It's actually confusing them here with buildings. Now, this is a big challenge because recognizing roads and sidewalks are actually something that we think we're very good at. If you were to take that initial model that was trained and evaluate it, it had very high pixel accuracy at recognizing roads. So the fact that it can degrade egregiously in this case is an issue that needs to be clarified and illuminated. There are other circumstances under which models can fail. Like, for example, if minor corruptions that hadn't been seen at training time appear. There's a data set that was introduced in 2019 that showed that even for the same exact data that was being evaluated before and after corrections, you could see up to a 20% drop in accuracy. And then, of course, at the extreme example, if you have a malicious actor in the loop, they have the ability to make minor perturbations to images that have dramatic impact on the results of your predictive performance. So classically, the adversarial examples, the hallmark of them is that small, seemingly noise-like images, very low magnitude, in such a way that once you've added them to the original image, they aren't going to change the perception of the image to a person, but they change, those noise images are selected exactly to be able to modify the predictive output of a model. There's been lots of study into this work, including at this conference. There was a workshop just yesterday that were looking at this problem as adversarial robustness and robustness more generally. So there's all of these different ways in which models can fail as a result of the data input or visual appearance changing. And it can change for many different reasons. It can change for benign reasons, like a curation or a capture bias, as it did with the still images to the video. Or it can change for subtle reasons, like corruption happened to images, or even an adversarial reason. A lot of these works that I showed so far focus on tasks like classification or more broadly just visual recognition. But visual recognition tools are also used as part of a larger pipeline. So one work that I want to highlight briefly is a benchmark to understand how corrections to the input of your visual space, when included as part of an embodied agent pipeline, can reduce the performance. This is something that isn't necessarily, we study these things in isolation, but again, if people are going to be taking weights from an initial model and adding it into a larger pipeline, we need to understand how they might degrade. So just very briefly, for those who aren't familiar, in the embodied navigation task, there's usually two different goal tasks that people study: point nav and object nav, navigating either to a point of interest or an object of interest, like go to a sofa. The agent will have input to just sensory information like RGB or RGB in depth images shown here. And this top-down view is just shown for visualization. The agent doesn't have access to a map. It's just reactionary depending upon its visual inputs. So the agent will be given a goal task like traveling to a particular point. And it will then, once it travels to the particular point, it will be rewarded if it reaches it in a timely manner. So one of the issues with these benchmarks that existed today was that even though it appeared that you were having very, very high performance, so these agents were getting close to 100% success rate on some of these tasks, if we analyze how they're being used from training to test, what is actually being modified, it was mostly focused on scene layout variation. And let's focus on what would happen if something changed in our sensor, meaning our visuals changed, or if something happened to change anything with the dynamics of the scenario. So in this robust nav benchmark, what's being introduced is an ability to understand, evaluate, measure how the performance might degrade in response to changes in the visuals. Some examples of the corrections for the visual space include things like what were to happen if there was motion blur, or lower lighting conditions, or if there were debris that ended in the camera. For dynamics corrections, there were really just two different types. One that emulated things that would result from an environmental shift, like a change in friction of the floor, or things that would be a result of the agent itself having a malfunction. So once we do that, oh, for some reason the videos aren't playing. Just imagine that there's a video. I'll describe what it would show. So in general, what would happen is the agent would be able to perfectly navigate, both successfully but also quickly, to the target of interest. And just checking. And once you change some of the input visuals, even something as simple as changing the lighting conditions can make the agent have difficulty to navigate to the point of interest. And for some corrections, it could fail entirely. So the reason why I bring this up, the difficulty here, is that this is yet another scenario where we have a benchmark that is trying to establish some measure of generalization. But as we start to get higher in performance and gain some confidence in the performance of the system, it's going to be more and more adopted and reused out of the box. But we need to be careful to make sure that we actually accurately represent the expected performance in all deployment scenarios, which may involve changes to your sensor. You may get a crack on the camera, or spatter may appear, or the friction of the floor may change. And so as we continue to think about, we know the ways that models can fail, we need to make sure that we properly are evaluating them before they're going to be reused widely. Now, of course, this is a simulated environment, and frequently in computer vision, we do use simulated data. And the reason why we use simulated data is it's going to be much cheaper to be able to use in practice, and it might allow us to actually generate all of these scenarios that are potentially going to be experienced at deployment time, both for evaluation, as was done in robust nav, but also for training. But there is a gap between simulated data and real data. So one thing that we have to take into account is any performance that we evaluate on our system in simulation these text to be used out of the box on real data. One popular example that's used within the domain adaptation community is to think about training on synthetic driving data, like from the Grand Theft Auto game, and then adapting it for use in real data, like on the cityscapes data set. More broadly, domain adaptation is the problem statement where you have access to a large labeled source data set. It could be from your curated data set like ImageNet, or it could be images that you have access to in a product, or it could be your same data. In any of these cases, the idea is that you have to be adapted or specialized when the visual appearance changes. And this appearance change can occur, again, because of something like capture or curation bias, or it can be because you would like to be able to recognize these objects as they appear in the wild, or because you want to be able to take your simulated model and use it in the real world. So if we're thinking about the fact that these models degrade, these models aren't working as well out of the box, maybe there's something we can do about it. Maybe we can actually start to adapt these models in response to observing changes in the visual world. A really popular class of techniques in this space is called domain adversarial adaptation. And the way that this works is that you imagine you have access to a large labeled source data set. This is going to be that model that you reuse over and over again. And your performance is quite high in domain for this source data. The challenge is that your performance degrades on this different visual appearance, this target data. And so we'd like to mitigate this problem by performing an alignment in feature space. The way that we measure whether or not the two distributions are aligned is we can train a domain classifier whose job it is to distinguish between features from the source and target domain. If you can distinguish the two, then the distributions are far apart. So we'd like to resolve this. We want the distributions to be aligned, because if they're aligned in this feature space being used for the supervised tasks of classification in this case, then we have a better chance of being able to use it out of the box on our target data. So to update this in order to align the two, we're going to use an adversarial loss, which tries to confuse this domain classifier, thereby rendering the two domains indistinguishable. There are many Zoom notifications coming up. All right, so once we do this, we have a simulated image. And the simulated image, in this case, is from the Grand Theft Auto dataset. And what we're going to do is we can perform image-to-image alignment using something like a cyclogan in order to produce an image. You can use full domain space in order to produce a model that allows you to better evaluate or better adapt your simulated model for use in the real world. So this is an example where you have a cityscapes image in the upper left-hand corner with the ground truth in the upper right-hand corner. Before adaptation, meaning just looking at your model out of the box trained in simulation, it doesn't work very well. After using this type of domain adversarial alignment, you're able to start to see improvements. And in particular, what I want to highlight here is that a lot of the improvement actually comes in the form of the classes like road. You do have some extra improvements here, like this pedestrian or the street sign in the background, but the majority of the improvements, and then we see this over and over again, actually comes in the form of the head classes, or the classes that are most prevalent in the data set. So for an application like self-driving cars, the most prevalent pixels for semantic segmentation are the ones that are going to be corresponding to road or building. And so that's where we see most of the improvement. And actually, you see relatively less improvement on the rare classes. And this is an artifact of this type of alignment technique. But when we're talking about real world applications, we're talking about people trying to use these systems for adaptation out of the box. The difficulty here is that your data set hasn't necessarily been curated. So this limitation of using marginal statistical alignment techniques is a real one that we have to contend with. It means that our rare classes are not going to be as well adapted. It means that overall, we're going to be biasing our adaptation towards the common classes. So coming up next, I'm going to have Viraj step up here, and he's going to tell you a little bit about what we can do to help mitigate these performance losses when you have the situation of a long-tailed distribution. We'd like to move beyond this idea of marginal statistical alignment techniques and instead start thinking about how we can do alignment that more and the rare classes.
Okay, so thanks, Julie, and I'm Viraj. Excited to be here, and I'm going to be continuing talking about the problem of adapting models to label imbalanced data so that you don't end up with poor performance on rare categories that may still be really important from your application's point of view, and so that you have more reliable computer vision systems. So in the real world, as you mentioned, you may be able to curate your source data sets to say have a balanced label distribution, but we really don't have any control over the target data set. And in fact, many real image data sets, as shown on the right, tend to have a long talked about actually have been shown to because they Sorry about the technical difficulties. So as I was saying, so we have the boundaries are shown in gray, and some instances like this triangle that you see on the left and the circle on the right are actually misaligned, right? And if you try and do self-training here and say perform entropy minimization, you're going to actually increase the model's confidence in its own predictions, even if they are incorrect, and push them away from the decision boundary, effectively reinforcing model errors and leading to this kind of domain misalignment. So the main challenge here is that the model is being adapted in response to all observations, but the goal is to try and adapt only on reliable observations that have a high probability of being correctly classified. And we explore this idea in, sorry.
our
Yeah, now right now it's Wi-Fi. I don't know. Yeah, no. Yeah, let me try to. You can.
Should I switch off my video?
Yeah.
Should I keep my video on?
No, you just take it off.
Take it off.
Yeah, I think it's already on.
All right, sorry about the delay. So I'm just keeping, for people on the call, I'm just switching off my video right now because the internet connection is quite unstable. Hopefully that'll help. So as I mentioned, we're trying to identify reliable target instances on which to self-train. And one way to do that could be, say, model confidence, but that's been shown to kind of be unreliable under a distribution shift. And so we instead use this notion of predictive consistency across image augmentations, which I'll make more concrete in a couple of slides. And so we can then go on to identify some target instances here, shown with this green tick, as reliable and others as unreliable, and then only selectively increase model confidence on consistent instances or reliable instances and reduce it on unreliable ones, hopefully leading to more robust domain alignment. So here's how the algorithm operates. So first, you start out by sampling this a labeled source image, in this case a sketch of a bear, and optimize a supervised loss. And then you sample an unlabeled target image and get a prediction from the model. In this case, it also predicts that it's a bear. We then apply a committee of label preserving data augmentations to generate these images that you see here and get predictions from the model. And you'll notice that the model prediction in this case actually changes to dog. And we can pass all of these to this selective entropy loss, which operates as follows. So it's simply going to measure the predictive consistency across all of these images and use a simple majority voting scheme. And for instances for which the predictions are mostly consistent, it's going to mark those as reliable and minimize the model's predictive entropy to increase confidence. And for unreliable instances, we can maximize entropy to reduce confidence. So that's the entire approach. And you may notice that it's like relatively simple compared to, say, some prior work on domain adaptation via adversarial learning. But the main notion and insight here from a domain adaptation point of view is to introduce this notion of instance reliability and only do selective adaptation. And that can lead to much better performance, especially on underrepresented categories, which are particularly important from a reliability point of view. And so as results, we look at the standard classification benchmarks, such as this 40-class subset of the popular domain dataset, which is natural data distribution and label distribution shift that you see on the left. And here are some of our results on 12 shifts from this benchmark. And we're interested in transfer performance to the target test set. And we're looking at per class average accuracy. So first, we know that a model without any adaptation, that is just trained on the labeled source data, gets 66.8% accuracy. And we benchmarked some baselines based on distribution matching and meant to overcome just label shift, and find that they do not offer very strong improvements. And then we look at some recent methods that are meant to counter both data and label distribution shift based on relaxed distribution matching, confidence-based self-training, and entropy minimization with other losses. And we find that the self-training methods in particular are a little more robust. And finally, our method, we find, does much better in this particular setting, and also sets a new state of the art on most of the shifts that we study. And in follow-up work, we try to extend this to a more realistic and complicated task of semantic segmentation. So seen here on the top left is an image from the Cityscapes dataset, and we are trying to do adaptation from the Grand Theft Auto game to this Cityscapes driving dataset. And here is the ground truth annotation for this image. So before any adaptation, taking a model that's just trained on the source data set, this is what the predictions look like. And if you go on to apply unconstrained adaptation on all of the model's predictions, so you self-train on all of them, this is what you get. And you notice that the model's performance is measured by mean intersection over union does go up. But most of these gains are on well-represented categories like road, shown here in purple. And if you actually zoom in on tiny objects such as the street sign here, performance actually degrades when you do unconstrained adaptation. But if you do selective adaptation using a similar algorithm as I was describing earlier, you can actually recover performance again on these small objects categories and also boost overall performance substantially. And in very recent work, we tried to kind of validate the same pipeline in a more modern setting where we try to adapt vision transformer models initialized with self-supervised representations, which is rapidly becoming the de facto pre-training strategy for deep models. And we, in particular, methods like the masked autoencoder approach that was recently introduced, which learns to reconstruct an image given a highly masked version of the same image. And as before, our idea is to use predictive consistency. But we find that in this case, a superior alternative to using random augmentations is to instead match the self-supervised proxy task. So in our case, this corresponds to consistency under masking. And so we can actually do attention condition masking by leveraging the VIT attention mechanism to generate these sorts of masked images that you see on the right. And then you can probe the reliability of this target instance by measuring predictive across all of these images. So far, we've been talking about performance degradation from bias in the form of curation and weather and sensors, but a less studied bias is one with changing demographics when systems underperform on underrepresented subpopulations. So prior work by Dries et al. Has shown that many modern computer vision datasets significantly overrepresent the developed world. And for example, for ImageNet, most of these images were collected primarily from North America and Western Europe. And that clearly is in stark contrast to the distribution of world population shown here in the bottom right. And this is a problem because models trained on these data sets then go on to massively underperform on images from underrepresented geographies. So because these models have primarily seen soap look like this image that you see here on the right, this model, when evaluated on a bar of soap from Nepal, the model will mispredict it as things like food and cheese and bread. So far, since we've been talking about domain adaptation as a way to match representations between the train and test sets, we tried to ask whether domain adaptation can fit this setting and help make object recognition models work for everyone. And this was presented at a workshop earlier today. So the goal is to take models that are trained to recognize, say, statues from North America, shown here on the left, to also recognize statues from Thailand and South Africa and Vietnam, which currently the model is not doing very well. And to do this, we collected two geographically diverse benchmarks based on the Dollar Street and GeoIFCC data sets. So, and here source and target represent geographically distinct locations. So, and you notice that even for a simple category like toothbrush, visual appearances can change quite significantly across geographies. So how do existing unsupervised DA methods fare? So first, we set up two adaptation settings, for instance, from North America and Europe to the rest of the world, and measure the performance of a model trained and tested on the target set, and a model trained on the source set and tested on the target set. Performance gap between the two is what we're trying to close. And we applied some off-the-shelf unsupervised DA methods, but unfortunately found that they offer limited to no improvement. And so off-the-shelf methods just don't seem to work in this setting. And when we probe this further, we find that this is because of the existence of additional challenges beyond data distribution and label distribution shift. So the first is this notion of context shift, where object surroundings can change a lot across domains. So you'll see toothbrushes primarily in bathroom environments in North America, and there's a lot more diversity in surroundings for the same category in your target. And the second is a notion of subpopulation shift, which is a shift in intra-class distributions for a given category. So, for example, for a category like cleaning equipment, it primarily means images of vacuum cleaners in North America, but it primarily corresponds to images of brooms and mops in other parts of the world. And this shift in intra-class distribution also poses a challenge to adaptation algorithms. So to conclude, I think we need to call on people to develop more specialized solutions for this geographical DA setting. So that's all from me, and thanks for listening. I'll hand it back over to Judy.
Thanks, Raj. So I just want to conclude very briefly. We talked about a lot of different things today. This is a tutorial. We're talking about human-centered computer vision. This particular talk is focused on thinking about ways in which we can make sure that our vision systems are more reliable for use for lots of different scenarios and lots of different people. People are going to take our models and use them out of the box. And we'd like to make sure that we can have some measure of a reliability goal. We want to make sure that they're going to work as expected at deployment time. But this can mean many different things. This can mean that you want to make sure that it works as your appearance changes in subtle ways, like because of the weather changing. You'd like to make sure that it works even as malicious actor intervenes. And you'd like to make sure that it works for all people around the world. So these are the different scenarios, and each one of these scenarios might necessitate different mitigation efforts. The first thing that we would like to say in conclusion is just that we need a wider diversity of benchmarks to be able to capture and measure all of these different sources of variation and different ways in which our models will be used. And then we need new algorithms that allow us to introduce a sense of resiliency to our models. We want them to work out of the box as much as possible, but we also want to be able to specialize them or adapt them. And especially we want to be able to do this in a reliable way that can be done without needing to have an expert in the loop. So the two works that we highlighted here today, if you're interested to look them up, was a benchmark for robustness in embodied navigation, as well as an algorithm for adaptation, especially for adaptation in long-tailed or labeled distribution shifts. I want to thank Raj especially for being a co-presenter, as well as the other members of my lab who have contributed to some of the work that I highlighted here. And I think that we have a few minutes for questions at this time. Anybody have any questions? There's a very bright spotlight right here, so if anybody stands there, you might have to like wave. Okay.
Thanks for the talk. I was wondering if you have data on how commonly directly reused software versus creating from scratch. Like how many people learn directly reused software?
So what I would say is this. It's very, very common within our community as we design new algorithms to download weights of models. If you're in a company, you might not download weights. You might be training from scratch on data that you collect, but you're going to be having a similar problem that exists here, meaning that you're going to have an initial data set that's large, and you're going to be reusing those weights for new circumstances. And if you're not a giant company that has a large annotation budget, you're going to have to be doing some sort of reuse of other data.
Thank you so much for supporting. We struggle a lot with measuring relevance given times, but how to keep it close to say, hey, this model in the wild is biased versus the gas. It's categories. It's even more complex if it's a repeat of when we have like giving data point to distribution or anticipation where we can probably repeat of this automatically measure the bias in the real world scenario. The first question is, in the wild, how can we measure the bias beside having luxury of categorization kind of problem? The second question is, what about CGI data where computers really use? In the retail world, we need every Wi-Fi technology. What are your recommendations to take into account the fact that we have these images during this training? Keeping into account that today is highly only in scale data. How can we generalize the training model taking into account? These images are white. In the wild, you will see very, very complex. Congratulations on bringing it here.
Yeah, so thank you for the question. There's a lot of interesting points in there. I'm gonna, it was a long question, so I'm gonna reiterate 2 points. One of them, which is how do we measure bias? That's a great question and a hard question in general to answer. And we didn't have time to talk about it in today's tutorial, but in general, my personal belief is that we need to have some better ways to illuminate bias in an unsupervised way. So we need to be able to automatically identify parts of data, or even when we receive new data, have a sense of reliability there. And if we don't have that, then we're kind of stuck in the scenario where we have to pre-annotate all sources of variation and then use our standard tools of validation with benchmark systems, which we know is sort of fraught. We do need benchmarks. We do need that to have kind of a more robust measure of how well we think it will work across different scenarios. But at the same time, if we want to truly understand bias and predict what's going to happen in any individual scenario, we need to have something that will work more on instances. And the other question, let's see if I can remember it. Do you remember the other part of the question? Anyone remember? Oh, yes, right. So the other thing is, and I encourage you to look up the topics of domain generalization, which we didn't talk about today. But in brief, the way that works is that you're pre-assuming that your data kind of is, you want it to have enough diversity or a large enough set of options that can perhaps match what you'll see in any test time. So for example, with your white background, you know that this doesn't mimic what you're going to see at test time. And so some of the things, like the simplest things that you can imagine doing, is doing some sort of augmentations. And there's a rich literature, especially in the robotics community, on doing different domain random augmentations to be able to use low fidelity simulated data or data that has a white background, and then reuse it in scenarios that have more complex backgrounds. And surprisingly, so far, it seems like you don't even need to have hyper-realistic augmentations in order to get the value of these approaches. What's most important is just that you kind of break the idiosyncrasies of the initial data set. So making sure that there isn't a large swath of only white. Even adding some kind of like random color blocking and noise helps break the learning of some of those features. Okay. Oh, one more question.
This is just a sort of general question. So I often see computer vision class that we tried to do the example you had with bar soap from Nepal. But how likely is it that I'm going to see that in isolation from its environment? So the more realistic situation seems to be that if I'm in Nepal and then I can see it. And I will guess when I'm in the bathroom, given that there's nothing else, there is soap like atmosphere soap, right? So I'm just curious as to how you would factor that in. I mean, We have set up a lot of computer vision tasks as Xception is sort of superhuman tasks that don't have to do with what humans actually
Yeah, so that makes sense. I guess, and that example in particular, I think might be quite, it's kind of cherry picked and it's particularly challenging. So what we were trying to do in that specific setting was to see if the model has only seen, soap images from, say, North America, and it has seen very few examples of bars of soap. Then is it able to also generalize to bars of soap from other parts of the world? Context and the surroundings have changed quite a bit without access to labels, but you do have access to the data, right? We're still trying to align the features for these two domains without access to labels. And I guess the intuition is that, then you can perhaps deploy your model in novel geographies without having to collect a large data set for each setting. And at least from our preliminary findings, it feels like doing it in purely unsupervised fashion is really challenging. And that's kind of, to your point, maybe we do need to collect some labels in the target as well, if not for the entire data set, at least for a subset. And maybe that's sort of a more tractable task to solve. Right.
it might make the problem less artificial. And this is I'm being very critical here.
Right.
I'm not saying that perfectly fine.
Right. Yeah, that makes sense. Yeah, I think in general, having more information in the form of a taxonomy in your label space or having more annotations per image, having any labels at all to begin with, or metadata in the form of where this came from so that you can learn like different representations. All of those are perhaps sort of ways towards making this task more tractable and also not like expecting too much from our models. Thanks for the question.
Okay, so let's thank our speaker, Viraj, and Professor Hoffman.
We're running all of this through one. You don't have another USB-C. That could be the problem. We're asking too much out of that one dongle. But you've got, as long as you've got plenty of power, but now it's wow, I've got green light now. We didn't have that.
We are on Ethernet. Okay, so I will be the second speaker. Let me first introduce myself. I'm Bode Zhou. So I'm an assistant professor at the computer science department, UCLA. So I joined UCLA early this year. So before that, I was a faculty member with the Chinese University of Hong Kong. So I got my PhD from MIT in 2018. So my research is on computer vision and machine learning. So I've done many different works from visual scene understanding to recent generative modeling and machine autonomy. So today I would like to share with you some of my thoughts on human AI interaction. And so I think that is a very interesting topic especially for this kind of topic can be done in a research lab versus these companies. So nowadays, we see many real-world applications of AI and computer vision, from self-driving to whole robots to healthcare. So in different AI applications, so you can notice that there are always two counterparties. For example, in self-driving, we have the driver and the autopilot AI system. In the whole robots, we have the elder people and also the robots. Also for this healthcare medical decision making, we have the physician, human doctor. We also have the medical AI. So in this real world applications, so we always have the two counterparties, human and AI models. So I think it's very important to build trustworthy interactions between humans and AI. We really want to use and deploy those AI models in reality. On the other hand, AI is also achieving the human level and the superhuman performance from image classification. So we are using deeper and larger network to improve the performance. And also for image generation, so we have this GAN model as well as recent diffusion model that can synthesize photorealistic images. Also in many machine autonomy applications, such as this very complex strategic games. So those AI model trained from reinforcement learning can outperform human best players. Also, we have the AIs that can steer the vehicles in real world. So this kind of superhuman performers actually generates narrative of superhuman AI taking over humans. So people start worrying about these machines will take over a lot of human job opportunities. Also, we may create some this monster AI that may threaten the humankind. So here I would like to argue that our relations with AI models shouldn't be always adversarial or competitors, right? So we are the creators of the AI models, and we are also the user of those AI models. So we want the AI model can better empower us and augment our human capabilities and offer more possibilities for us. So think about the inventions we have. For example, the airplane. So we invented this airplane that can help us reach the destinations faster and in a safer way. Also, for this invention of telescope. So we use this telescope to observe the things we cannot observe before. So that's why I think it's very important to make the AI models as a human-centric. So the human-centric AI is more like a reframing the relations between AI and the humans. So in this computer vision field, so I think people care about performance of the AI model. So we spent a lot of efforts that try to develop better AI models to crush the benchmarks. So at the center of the development, so the algorithm is the center. Then all our researchers try to develop deeper and larger models to crush the benchmarks. But if we shift this perspective from algorithm-centric to human-centric, it puts humans at the center of all the research and the developments. So then we can ask more interesting questions and more practical, useful questions, such as how AI algorithm can better serve humans and make our life easier. So for this kind of human-centric AI, so one very important concept is this human control versus AI autonomy, right? So you may wonder this relations between human control and the autonomy is sort of binary relations. So if we want to have high human control, then we may have low AI autonomy. So if we want to have high AI autonomy, then we may have very low human control on that. But I will argue that the relations between the human control and the autonomy and not necessarily being the binary relations. So we can have actually two dimensions to represent the relations. So here I show you a plot. The horizontal axis is the machine autonomy. So we have low and high machine autonomy, and vertical axis is a high human control and the low human control. So let's say our ultimate goal is to build reliable, safe, and trustworthy AI systems. So it's at the upper right corners. So we want to go through that directions. So there are actually already some human inventions in that domain that have high machine autonomy as well as high human control. For example, the elevators and the digital cameras. So we have many settings. We can customize the machines as we want, and then we can click a button, then this elevator will send us to the floor we want to go, or this digital camera can take a photo for us. For the another hand is the high human control and the low machine autonomy. We also have such human inventions, such as bicycles and the pianos, right? So they are have no machine autonomy, so human have to be there, but human have to spend years of practice, then they can master those skills and enjoy interacting with these machines. We also have this low human control and high machine autonomy inventions. For example, we can have this airbag and pacemakers. So those inventions, so as ordinary time, so we are not aware of their existence. Only when something happens, then some accident happens, there this airbag will engage. Then so it works in a fully autonomy way, but with low human control. We also have this low human control and the no machine autonomy, such as music box and the night mice. So I will argue that so our goal should go from the current AI system that have medium machine autonomy and no human control towards the upper right corners, towards this reliable, safe, and trustworthy AI system. So there are two ways we can go there. So one is we can spend a lot of efforts to pushing this AI system horizontally. So that the efforts we pay to develop new AI models and algorithms which higher performers on the benchmark. I think we also need to pay effort of developing this human controllable and the human interactive AI. So we will do the efforts towards this vertical axis can finally lead us to our goal that build a reliable, safe, and trustworthy AI system. So in this lecture, I will give you several examples, like how can we build this trustworthy and relations with between the human and AI. So in different computer vision tasks, from the image classification to image generation, to recent this machine autonomy embodied AI applications. So here I would like to think on those AI models used in different computer vision tasks as some pets. So we may have this human AI interaction. So I will make this analogy to this human dog interaction. So those models we trained are more like our pet, right? So we train them well. Then this dog can do a lot of tricks, can listen to your orders, like sit and down, and then you can fetch the object you want. But sometimes this dog will also don't want to obey your orders. So then some troubles and making mistakes. So we have to give them guidance on how to do that. Also, sometimes we may have to babysit this AI model we have to improve their capabilities. So here, the first part is the classification models. So people train a lot of image classification models. So we want to build the relations with our AI models. So the most popular ways is this model interpretability and explainability, right? So it's a rising topic in this field. So we humans want to understand what's going on inside the neural network we trained and why this neural network give us a prediction. So Ruth Fong will give us a lecture in the following talks. So I want to talk more on this topic. But on this image classification, I think another very important topic besides the interpretability is this AI-assisted decision making. So here is the work published at Nature Medicine. So it tried to examine the different AI models and how those medical AI models can be used in this clinical experiment to help the human doctor make decisions. So they take this AI model trained for skin cancer recognition and see how this human doctors can use this AI model to make an informative decision. So they discovered that when using this AI models in this human decision making, so human doctors can make more informative decisions for our patients. So I think that kind of human AI interaction for medical decision making will be a very important future direction, because we cannot like totally replace our human doctor medical experts. So we have to build this human AI in the loop, human decision making. So that is the part for image classification. Then we'll take shift to the second part is image generation. So how can we build relations with the generative AI models? So generative AIs is a hot topic, especially in recent 2 years. So we have this style gun that can generate realistic images. So for this style gun models, so when we train on large number of images, then this model can take input vectors, then it can generate a lot of realistic images. So the results, image quality are very good. But the question here is how humans can use the generative AIs to edit and create our own images. That's what we care about. It's not about how good this AI models can create the image. So we care about how this generative AI can use in this content creation and content editing applications. So for example, here we want to have AI assisted content editing. For example, we want to use the GAN model to edit my own image. So we develop some GAN inversion methods that we can copy and paste my face on the celebrities. Then we are doing some diffusion process, then we can put my face inside. So that lead to problem called GAN inversion in this field. So here is a survey paper we write on this GAN inversion. So because the GAN, after your training, so you have the generator, then you can generate a realistic image. So if we want to edit our own image, so we have to do this optimization problem by giving this a real image. How can we recover this latent code? Then can reconstruct the image using the generators. Then we can do a lot of latent manipulations. Then we can change the attributes of the output. So we want human can want to change certain attributes. So people develop different methods such as interface scan, GAN steerability, and high GAN and CBOT. So different methods that they want to do this kind of latent manipulation. So basically, they discover these latent boundaries correspond to a certain human understandable concept. Then we can add those vectors on top of the original latent vector. Then we can edit the attributes we want. But one limitation for this kind of latent manipulation is that for each attribute, we have to train this latent boundaries. So to address this issue, so researchers come up with different ways to input our human intentions. For example, here I list the two work. One is a style clip, another one is a diffusion clip. Those models try to combine this image language model, clip model, with this image generators. So in that sense, when people input some text, then this text will be turned into some latent vectors by these clip models. Then this information can be input into the generators. Then we can control this generation process. So this text-guided image generation allow people have better control on this generation process. Another huge progress is recent this OpenAI DALL-E 2 text-to-image models. So in that sense, the human intent can be conveyed through the sentence descriptions. So because human use sentence to describe a lot of things. For example, here we can input a sentence an astronaut riding a horse in a realistic style, then the study 2 will translate the sentence into a certain image. So if we change the input sentence, then the study 2 will output a different image. So here the input is an astronaut riding a horse as a pencil drawing. So it will change the style of the content. But one issue is that you can see the content still change, not like we are doing cell transfer. So the overall content already changed when we have a different input. So you can also change another input, an astronaut playing basketball with cats in space in watercolor style, that can generate this very beautiful watercolor style image. So this kind of text-guided image generation really allow human to input their intent to the generative model using the text. So the DALL-E 2 models is a combination of several large-scale AI models. It's a combination of the CLIP and the diffusion model, as well as the most important is the huge amount of text image pairs. So it contains more than 250 million image text pairs. Then after the trainings, then people can input any sentence, then recreate the image. Despite all those amazing synthesized performance, there are still some limitations from the perspective of human contributivity for the diffusion model. So if you take a look at the diffusion model, so it's an iterative process. So each time it will add some noise, it will be noise from the spatial image, and gradually you can create the contents. So the generation process is considered as a noising process, but the issue is for this iterative process, it's really difficult to control the contents. Let's say we want to change the view of the image or change a certain attribute, like global attribute, like the lighting or the age, gender of the person, so you really have to implement that. So to improve this contributivity, so people develop some classifier guided diffusion sampling. So what they are doing is that they introduce some classifiers on those noisy image in the intermediate generation steps. So they input the generated noisy image into the classifier, then use gradients of the classifier to guide it, the generation process. So on the right, I show you some images that generated using this classifier guided diffusion sampling on an unlabeled diffusion models. You can generate very nice images for certain categories we want. So for image generation, so we have many other ways to convey the human intent to the generative model. So people have developed the Gaussian that we can input the semantic mask to generate the things we want. Also, we can use a stroke and a brush to input our human intentions. Also, people use a sketch to express our ideas to the model. So I think that is a very interesting direction. How can we develop different flexible way to input our human intent to the generative model? So ask the generative model to generate the things we want. So here is the recent work we have doing for this. So we want to have more spatial control on this image generation process. So previously, this generator will take a latent code and then generate the image. But sometimes we may want different spatial locations of the foreground. For example, we want this output cat move its head a little bit up. Also, we may want this cat to move its head on the right. So current generator doesn't support this kind of spatial control for this image generation. So we developed some work that use to introduce some spatial control on the generator. So we follow some self-supervision of spatial key points in the generator. So basically, we design some spatial inductive files in the generator that can learn to associate with certain activations in the generator. So the issue is how can we create the supervision? So here we utilize the discriminator, because the discriminator after training, so it contains a lot of class specific information. So there is a tension map inside this discriminator, then we can use this emergent class attention map to as a supervision to train this spatial key point we have. So we create this self-supervision loop. Then we can train this special inductive bias. So after trainings, then we can have this kind of interface. So user can have this use mouse to move around the key points. Then we can change the locations of the cats. And this kind of spatial control can happen at different levels. We have 3 levels. So here is the intermediate level. So we have this more fine-grained control on this generation. So here is even more fine-grained control on that. So this kind of spatial control allow us to have to move this object inside the image around. So here's another, we add this spatial control for building generators. So we can move around, user can move around these buildings and change different parts of this object. So then we can keep overall content the same. So this kind of introduction of interaction into generative model allow us to create the content we want. So this kind of generative model can become more playable. So here I show you a work from Snap. So they built some playable environments on top of the nerve model they trained. Because in the video, so you can collect a lot of videos, then you can train some video generation model. So if we can condition on this video frame generation on the human actions, then we can actually make this generative model and generate the videos that can be controlled by our humans. So here, human can actually click the buttons, then we can control the players in this generations and make it more like an interactive and playable environment. So that is also a very interesting direction to make our generative model more interactive. So that is the second part for this to add this image capabilities for this generative model. So the third part I will talk about is this how can we build human AI interaction for this AI model trained for this machine autonomy applications. Because nowadays, so there are a lot of excitement in this embodied AI. So we train this embodied AI to accomplish a lot of tasks. For example, we can train some driving policy to drive inside the environment. We also can train some reinforcement learning agent that can navigate inside this indoor whole environment. So they can navigate to certain locations. So here I try to train some this embodied AI model, try to learn a visual model driving policy using this very popular learning algorithm. So it's a reinforcement learning algorithm. So it just build some interactive environments, then we can train this agent. But one issue with reinforcement learning is that there is no safety guarantees. So you can see here is a training agent. So just doing all kinds of crazy things inside the environment and cause a lot of troubles. So for this kind of embodied AI agents, of course, we cannot deploy and train this model in the real world. So we want to improve the safety and the reliabilities of this embodied AI models. So what we can do is that we can also build this human AI interaction. So we can have this human in the loop learning with the safety guarantees. So for this kind of agent and environment interaction, besides the agent and environment, we also can include the human in this loop. So originally, this reinforcement learning only have this iterative interaction between the learning agent and this environment. So there is no safety guarantee. So right now we include human in this learning loop. Then this human subject can help us to safeguard this active exploration of the learner. So you can think about this human as a parent or some guardians that can supervise this the exploration of the kids. That whenever some accident or danger will happen, then they will actively involve and then they will demonstrate the correct actions when something is going to happen. So this kind of human-in-the-loop learning method is very important for this kind of real-world applications of embodied AI. So here is the work we have done published at ICOR this year. So we have this real human in the loop. So here is my grad student. So he is training this agent, monitoring this training process. So at the beginning, so this agent has some explorations. So if this agent running into some trouble, then this human subject will involve and participate in this learning process and take over the control. Then it will show the correct action to the agent. So in that case, so we can ensure the safety of the exploration process. So here you can see, so we speed up after about 20 minutes of training. So this agent already can do something. So without the intervention of the humans, so it can navigate inside the environment, not so confident, but still can do some tasks by itself. So here is another one. We also tested this kind of human-in-the-loop learning in the color environments. So we built this human interface. So human can monitor this model training. So whenever this agent run into some trouble, then the human will take over. So after several minutes, so this agent already know to drive in this straight road, just several minutes. But still running into the trouble when trying to turning left. So human will involve into this process and will continue to demonstrate this learning process. So after about 10 minutes, then this agent already know how to drive inside this color environment without the human intervention. So that is very interesting because in this work, we even don't have any manual design for the reward function. So if you have any experience in reinforcement learning, so you will know this reward engineering is a very important thing in reinforcement learning. So here we just use the intervention as a supervision signal to train our agents to try to minimize this intervention from human beings. Then this agent will know how to do this task. So also there are some other work inside this embodied AI research. So here is the work I highlight from MIT. So they developed some environment for virtual hole. So they built this kind of watch and help. So it's a task that human will collaborate with this trained agent to accomplish certain tasks, like try to search for some object. Then the human will control some agents, then will collaborate with another agent controlled by the AI and to accomplish the task. So this kind of human AI collaboration is also very important future directions. Think about that. We have more AI models deployed in the real world. So we want better collaborate with the AI model to achieve certain goals. Another topic inside this embodied AI is this human AI shared autonomy. So we have done some work towards preliminary work on this direction. For reinforcement learning agents, so usually people just train this agent to accomplish this primary task. For example, for this Mojoko ant environment. So when we train this agent in the ant environment, then this after trainings, so this ant will know how to move forward in this autonomous way. So without any human interventions. But the limitation is that this agent can only do this task autonomously. If we want this agent to do some other task, like turning left, turning right, then the agent don't know how to do it. So to enable this kind of human AI shared autonomy, So we developed some measure called policy deception. So it's analogy to our previous work on this network dissection or GAN dissection, that we try to interpret the internal representations of the training model. So we want to identify those emergent knowledge alerted inside the representation. So here we found out there's an internal representation actually learn a lot of this behavior functions, such as how to roll the body, how to throw the front leg, and how to prep the left leg. So after we have this kind of labels for those internal representations, so user can simply activate and deactivate certain regions, then we can achieve this kind of human-machine teaming on this kind of sheer autonomy. So here is a demo video showing you that at the beginning we have this agent just moving forward. Now here, after we identify this controllable latent representations, then when user press some keys, then we will activate and deactivate certain regions. Then we can have this kind of control the behavior of this ant. So like a moving left, moving right, or just stop here. So we can make this agent more controllable. So here is another environment. We deploy our method. So here is another reinforcement learning agent trained inside this environment, just moving forward. So before the training, so this agent don't know what to do inside the. So before the training, so the agent don't know what to do. So after we training this primal task, so this agent know how to move forward, because the primary training task is just moving forward. But when we deploy this agent in some new environment, like full of obstacles, so this agent don't know how to navigate, because this reinforcement learning agent have very poor generalization capabilities. So after we identify these internal representations, then we can have this kind of human AI shared control. This human can just press a certain key, then we can control the behavior of this agents, like turning left and stop here and turning right, have this kind of shared control. So that will be very useful for a lot of this autonomy applications. So we can build this human priors inside the autonomy and ask the agents to listen to our high-level human orders to achieve this like a hybrid control. Okay, so that's pretty much for my lecture. So I think it's very important to have this human AI interaction. So we want to build this synergy between the machine and the human intelligence. We want to build this trustworthy relations with your AI models you have, like your pets. So here I also list a reading list about this recent progress in human AI interaction. Okay, so I will stop here. So let me know if you have any questions. Yeah.
Thanks for my name is about teacher, and I have been working on some interpretability and human interaction with machines recently. I'm quite interested in the two questions. The first one is, as we showed before, one class is the goal, the final goal of the human AI interaction is that we try to get a perfect model and perfectly mimic the experience of human beings. Is that correct or not? If the previous example that example show that there's not just only one solution for this case for some right? So if that's one question. Another one is that if the final goal is now to try to let the AI model perfectly mimic the interface, do you think it makes sense? That's just a definition I think for me. Do you think it makes sense that we involve the human beings to try to train the human beings to be familiar with how the AI model works? I'm trying to understand the right model to make it see instead of trying to get a perfect model to explain itself. Do you think that will also help into the work of human interaction?
Yeah, so thanks for the question. So your first question is about the primary goal of the training task aligned with the human intent. So I think that's a very important question. So that's relevant to this AI alignment problem people are talking about. Because sometimes when you design some task, you design some reward function, but it turns out this agent learns some other like short paths to accomplish tasks. So in that case, the reward function cannot correctly reflect the things we want. So I think there needs more work towards this direction, because not of the time it's very difficult to encode our human intention using some reward function or using some loss function. So I think there should be more like fine-grained supervision over this process, then we can achieve better goal for that. Another question another issue you talk about, so this AI actually can learn multiple solutions to solve the task. I think that is also a very interesting direction. So it's relevant to the diversity of the solutions. So like for our human beings, when we solve some problems, so we may come up with different solutions. But for the AI, like a reinforcement learning agents or some other like learning algorithms, so they are limited by the reward function we define. So I think that there needs more work towards this direction. Like how can we design better reward function or loss function that can parse our human intent into the learning process. The second question you talk about is about how human can learn from the AI model, or how can they adjust their behaviors, right? So I think that is also very important point. Especially nowadays, we have a lot of more and more this superhuman AI model. They have this superhuman performers. Then I think we are at the stage to learn from the AI models to solve some problems. So that can actually improve our capabilities to solve some issues. So I think I watched some videos, like interviewed like Ke, so which is who is a top Go player, Chinese Go player. So he played with this AlphaGo, and he actually said he learned a lot by playing against this AlphaGo, and they learn a lot of creative solutions to solve the task. So I think how can we learn from AI models will be also a very important future direction for this human AI interaction. Yeah.
Hi, just to my question is about the interaction of how we can teach the AI models learn self-driving. So how efficient is the signal or the reward compared with other, if I take same cost of time to labeling some data, or yeah, this is first one. Second question is how to handle unbalanced signal. For example, you just show up to 6 minutes to turn out those three, but it takes longer time to turn left. How to handle this?
Okay, so your first question is about the sample efficiency of the human-in-the-loop learning algorithm. So we actually found out compared to this pure reinforcement learning algorithm, so we are like 10 times, I think it's 100 times faster than this pure reinforcement learning algorithm. So it's actually quite efficient. So it's also relevant to the representation we use. So right now we are using this LiDAR, like a one LiDAR representation. We want to do this kind of generate the control signal from the visual representation, then there will be this representation learning problem. So that is another very important issue in this kind of embodied AI, like how can we learn better representations that can facilitate the final behavior, like control outputs. So I think those two parts should be coherent with each other, so we can have better representations and the sample efficiency can be greatly improved. So people can always come up with some like pre-training, like how can we pre-train this visual policy representation. So we actually have some work in this direction, like how can we learn some driving policy using some YouTube videos. So use this kind of pre-trainings then can give us a much better representation than this ImageNet pre-training. What's your second question?
About the unbalance.
Okay. Yeah, so the unbalance is also very important issues for this reinforcement learning environment. So I always have this trouble with this embodied environment, such as Gibson or other environments. So their environment is fixed, right? So they only have limited number of environments, and it's very easy for the agent to overfit the environments. I think recently there's some work from I think Allen Institute. They use procedure generation that they can generate more interactive environments. So in that case, we can control the distribution of the environments. Also, we can have much more diverse environments that can improve the generalization ability of the agents. Thank you.
Especially my question is, how do you quantitatively measure that a model interacts with human well? Could you please give us an example or intuition? Thank you.
You mean the policy deception?
It's a general question.
Oh, general question. Yeah, so I think we will evaluate the human interaction using the number of interventions because human budget is very limited. So we have to be very careful about that. So the number of interventions and also the how comfortable human can use this interface. And we want, so one thing we found out is very important to build an intuitive interface. Right, so because it's more like a game environment, so human want to play the game, so we want to make the game interface more intuitive, then they can better intervene this learning process. So we actually play a lot of games. My grad students play a lot of games, so they can learn this how to design better intuitive controls for this type of environment. Thank you.
Trust and explainability is often the top two factors mentioned in machine collaboration or AI interaction. Are there other things that are also important to
Yeah, I think trust is like nowadays we have a lot of this trust words machine learning. So it's become a buzzword. Like the interpretability. So I think trust is from the understanding, and if we can better understand what's going on inside the model, then we can have better trust. So I will say the trust is more like a goal of doing all the things. So if we can improve the transparency and then improve the explainability and the interpretability of the AI models, and also we can improve the generalization of the AI models, then we can have better trust. So this also the interpretability and the explainability, so those are the different attributes, like human-centric attributes of the AI models. So of course, there are many other attributes we also care about, such as the bias. We want to reduce the bias, and also the reliability things. So there are a lot of things we should care about for this.
Thanks again for the presentation. So from the demo, you showed that human teaches AI to drive. One observation I found is that human cannot give some level of feedbacks to the AIs like computers. So it may be not time efficient to teach the AI by human. Is there a way to solve this?
Yeah, so that's about how can we build this mechanism about human intervention. So here right now we have this active intervention, which means the human subject will actively monitor this training process. So that gives a lot of this mental stress to our human subjects. So it's also not that efficient. So another direction to go is we can develop some uncertainty inside this learning agent. So the learning agent can learn when it cannot solve some problem, then it will ask for help from humans. So from that perspective, I think we can improve the comfort of this human intervention. But I agree with you, like how can we better design this intervention mechanism? It's still an open problem, so we still need more effort for that.
Okay, thank you.
Okay, great. So if no more questions, so thank you all for, this is our first session. So the second session will start at 4 p.m. So we still have 2 lectures. So yeah. So this one is also open. Okay. Okay, so let's start our second session. So second session will have 2 lectures. So the first lecture is given by Professor Olga Roskovsky. So Dr. Roskovsky is an assistant professor in the computer science department at the Princeton University. So her research is in computer vision, closely integrated with fields of machine learning, human-computer interaction, and fairness. So she has been awarded many different amazing awards, and yeah, so look forward for her.
Yeah, sounds great. Thanks so much, Billy, for the intro, and thanks for everybody for bearing with us at the end of the second day of tutorials. I know everybody's starting to get tired, but thanks for being here. So I'll talk very briefly about fairness in visual recognition. I want to first of all give a big shout out to all of my, or I guess this is only actually even a subset of the students who have contributed to this, to some of the work that I'll talk about today. So first of all, when it comes to fairness in visual recognition, right, what do we mean by that, and what are kind of some of the reasons why we're working on this problem? So over the past about 5 years or so, as computer vision has started being deployed kind of all over the place, there started to be, it kind of started to work, but also there's kind of an increasing number of these sort of drastic failures or problematic failures of computer vision systems. And so this is things like computer vision model that learns to quote unquote increase attractiveness by actually manipulating skin color. So this was a photo app filter that was released that claimed to manipulate, that claimed to sort of increase the attractiveness of a photograph. Now, why somebody would do that is a whole other question, but putting aside that issue, in practice, what this model ended up learning is to sort of change your skin tone in an effort to make it more attractive. And that is obviously a very, very problematic behavior by the model. And then there's a lot more examples, right? So machines taught by photos learn a sex appeal of women. Facial recognition is accurate if you're a white guy. So this is seminal work I'll talk very briefly about later in the talk by Joy Belomini and Timmy Gebru that sort of showed that face recognition systems have very, very different levels of accuracy. So they work really, really well on faces of light-skinned men and work very, very poorly on faces of dark-skinned women. And this has a number of course, downstream applications and downstream sort of implications, including when facial recognition is used in high impact settings like criminal justice. And then, of course, a recent controversy on Twitter with a cropping algorithm that prefers lighter, slimmer, and younger faces. So all of these issues, right? They're very complex and they're really socio-technical. They go beyond just the algorithmic questions. And there's lots of excellent literature, like for example, the work by a colleague at Princeton, Professor Ruha Benjamin, called Race After Technology, that really grapples with the social implications of these issues, both the root causes and the downstream impact. So when we work on fairness, we simplify all of these socio-technical issues into a much simpler cycle. So we say, okay, there's some kind of human history bias and prejudice that's making its way into large-scale data that then becomes part of AI models, or it's learned by AI models, becomes part of AI decision-making, and then that becomes part of our history. And so the question that we ask from a technical perspective is, can we adjust the AI design to try to mitigate some of these effects, to try to mitigate some of this bias propagation? And so we can kind of look at different pieces of the cycle and think about what would it take to design interventions there. So for example, if we look at the large scale data piece, right? So the key there is that large scale does not necessarily mean fair representation. So there's sort of this tempting narrative of, well, I'm just going to take all of the data that's available on the web and I'm going to use that to train my models, and then I don't have to worry about fairness. But of course, there is all kinds of issues that can come up. perhaps simplest or most salient is the question of demographic diversity. And so this is the, again, the work by Joy Belamini and Deborah that I mentioned. So one of the things that they pointed out in their paper looking at the accuracy of face recognition models is that modern face recognition data sets contain primarily people of lighter skin. And by primarily, I mean 80 to 90% of these data sets were people with lighter skin. And so this does not necessarily explain fully the discrepancies in error rates of the classifiers trained on these data sets, but at least helps give you some sense of, well, what might be going on there. Well, there's a drastic underrepresentation of people of darker skin in these data sets. Another kind of tempting narrative that you might say is, well, okay, maybe none of this fairness stuff actually applies to me if I don't work on faces or if I don't work on people recognition at all. And that's not true for, in particular, for the reason that actually Biraj and Judy already talked about with geographic diversity. So these data sets contain photos coming from particular geographic regions and have an overrepresentation of photos coming, for example, from the US, and very few photos coming from, for example, the entire continent of Africa. And again, as Biraj pointed out and Judy earlier today, this leads to errors in even, for example, object recognition models that fail to recognize bar soap because they've been trained on US-centric images and they've learned to recognize only US brands of liquid soap as a representation of what soap looks like. And so these kinds of fairness issues can come up, right, even in something as seemingly innocuous as object recognition. And the part of the cause of some of this is of course, the lack of diversity or the stereotype representations that are returned by image search engines. And there's a lot of work pointing out how when you type a particular term into an image search engine, the results may be biased along a number of different dimensions. So for example, this is work from, it was published in 2015 in Kai that analyzes the image search results when you query for different occupations of people. So when you query for something like CEO, the results that you get tend to be, first of all, more male focused than even sort of the number of the percent of CEOs who are actually men. In reality, the search results tend to be even more skewed towards male. And in addition, give again this kind of Western stereotype portrayal of what a CEO looks like, how a CEO dresses, and so forth. And so, of course, when we use internet, the internet as a source of our visual data, we inherit a lot of these biases. So in addition to these questions of representation within data sets, there's also this very rich literature on data collection practices. And I'm not going to dive into this, but I would encourage all of you who are kind of interested in this space to engage with some of this literature. This has been published. If you notice, all of these papers I'm citing are basically 2020, 2021, 2022. This is very much a recent and growing set of works looking at things like privacy and consent and ethics of data collection, who is being included, who is being compensated for their work of taking photographs, what happens if sort of somebody takes a photo of you and posts it on the web, and then does that implicitly give consent for this photo to be included in a computer vision data set, and how do we sort of grapple with all of these issues? And in particular, how do we grapple with these issues in the international context where the legal guidance may be very different across different countries? But what I want to highlight is a couple of our works thinking about this question of trying to understand the biases of within large scale data sets. And the first one that I want to sort of again briefly highlight is called Revise. So this is Revealing Visual Biases tool. And so our goal here was to set out to develop a tool that takes as an input a visual data set and then reveals potential social biases in the data set. So the issue, right, is that these data sets are very large scale. They were collected from the web or wherever they were collected. And it's very hard to understand sort of what is actually in them, or do they have particular biases that we may want to be aware of when actually training models. And so the contribution, this was originally published in ECCV of 2020 and was recently accepted to HACCV this year. So the contributions here were trying to aid dataset creators and users by revealing biases in large-scale visual data, kind of in a semi-automatic way, where the tool sort of says, okay, here's a set of things that I found, and then leaves it up to the user to interpret or analyze or sort of intervene upon them. So in order to do this, we're leveraging the available annotations. So if there's any annotations available for the data set, we will use those, as well as pre-trained models if there's no available annotations, as well as census data. If we have, for example, GPS tags and grab census data and use that to compute some statistics of the data set. And the goal is to identify bias in the representation of objects, of people of different demographics, and of geographic regions. And then the tool also suggests some quick actionable insights to the user in terms of what they might want to do to diversify the data. So let me show you one particular example finding, right, and then we'll refer you to the paper to learn more. So here's an example finding. So the images here are the COCO data set. There's two annotations that were used. So one is gender annotations, and I will see here, so these are binarized, socially perceived inferred gender expression annotations. So this is a significant simplification of the concept of gender, which is of course non-binary, but here we are just looking at sort of binary labels, male or female. These are annotated on photographs by people who, basically mechanical Turk workers who looked at these photographs and sort of try to infer what the gender of the person might be in the photographs. And further, these are actually derived from image captions in an automatic way. So there's a lot of issues and subtleties and nuances with these labels. This is what we have available, and this helps at least give us some sense of statistics in the data set. The second type of annotations are predicted scenes automatically using the places model. So this was actually developed by Paul and his co-authors. And so this is, we don't have scene labels on these images, but we can run this pre-trained model to try to get those. So now here on the y-axis, I'm showing the output of this scene model, so the different types of scenes that were discovered. In the x-axis, I'm showing the fraction of images with this scene and images with people who appear to be male versus female. And so you can see some patterns in here, right? So things like outdoor sports fields and parks appear to have people who are predominantly male, and then shopping and dining scenes have people who are predominantly female. And so you may want to ask, right? So what does this mean, and is this okay, and is this reflective of the world at large? And as a data set creator, is this a kind of pattern that I am okay with, or that I want it to be represented in the data set, or do I want to sort of intervene in some way and rebalance the data set? And so there is a lot of work right now in computer vision fairness that says, okay, these data sets are going to be biased in particular ways. And for example, there's sort of gender bias in these data sets. So now I want to try to intervene upon this. And in particular, I want to train sort of models from these representations that are invariant to, for example, the concept of gender. So I want to train a model that is completely gender blind, that completely removes, gender cues from the data set, so I don't have to worry about gender bias in the models. And so I will show you sort of one result. So this is something that is part of the process we just submitted to archive. So I think it's not on archive yet, but it will be today or tomorrow. So we are looking at gender artifacts in visual data sets. And the question we want to ask is to understand actually the extent to which gender artifacts are present in the data set. So in the previous example, right, was revised, I showed you, okay, maybe people of different genders are more correlated with different scene type, but like, how prevalent are gender artifacts actually in a data set like COCO? And so what's happening here? So this is one result from this larger paper. So I'm showing on the y-axis the ROC AUC, so basically the accuracy of a gender artifact model. So this is a model that's trying to classify the image as whether it contains a person labeled female or male. Again, the images are the COCO data set, and the gender labels are the same as before. On the x-axis, I'm showing the different resolutions of the image. So as we sort of decrease the resolution of the image, you can see how it becomes sort of more and more pixelated and less visible, less and less understandable. So the different lines, so the blue line at the top shows color images at different resolutions and sort of the accuracy, right, of this gender artifact model on these images at different resolutions. The gray line is the same thing in grayscale. So what's the first thing you want to notice? So the pink line at the bottom is actually random chance at 50%. So for color images, even as low as 7:7 resolution, you're able to reliably predict whether the image contains a person who appears to be male or contains a person who appears to be female, right? Even at 7:7 resolution. And even more so, we've got this purple line, which is actually a model trained on just 3 features. So this logistic regression model trained on 3 features, which is R, G, and B. So the average image color of the image. And we're able to do, again, significantly above random chance in predicting whether this person is likely to be male or female. So what does this tell us? So this tells us that these gender artifacts, these gender visual cues that are correlated with gender are very, very pervasive in data sets like COGO. And actually, I mean, we've ran analysis on open images, for example, as well. So this suggests that if we're trying to build models that are mitigating bias in these data sets that are sort of invariant to, for example, gender cues, we have to be very, very careful because these cues are very pervasive and they're sort of everywhere. So any kind of simple intervention will not work to obscure gender cues. So we have to sort of learn to live with them. And so now we can talk about, right, so how do we, given that there is always some kind of bias in the data set, right? So we need, on the data set side, we need targeted interventions, right, to increase representation, to examine and understand the data, to constructively engage with the raised ethical issues. But ultimately, this kind of bias is always present in the data set. So what can we do on the model side? So what can we do to actually try to mitigate this bias? And there's a lot of things that we can do and a lot of challenges in building fair models, right? So there's work on trying to understand bias propagation. So I talked about these gender cues, right? But one question that kind of naturally comes up is, are they actually going to be harmful in downstream models? Like, first, are they going to be learned by downstream models? And second of all, are they going to be harmful, right? And so there's a line of work trying to understand kind of under what conditions this happens. There's a line of work looking at interpretability and interpreting the models and trying to figure out what it is that they've actually learned and are they relying on any of these, for example, gender cues or racial cues or whatever may be in the data set. There's a line of work on looking at being right for the right reason. So making sure that when you're making predictions, you are relying on sort of the parts of the image that are actually relevant to the prediction instead of on spurious correlations. There's a very rich literature on quantifying fairness. So how do we actually measure what fairness is? And how do we measure whether our models are biased, unbiased under different circumstances? Of course, very rich literature on actually mitigating model bias once we've quantified the metrics, right? So how do we actually implement this in the model? And finally, engaging with the broader social context. And I'll say actually right now, so the Fairness, Accountability, and Transparency Conference FACT is actually going on in Korea right now, unfortunately, simultaneously with CVPR, but that has a very rich line of work on sort of the connections, sort of the social technical connections between the some of the algorithmic work as well as the social impacts. So rather than diving into this, so I'll actually stop here because I will pass it off to Ruth, who is going to talk about interpretability, both in the context of fairness and much more broadly. So Ruth is an expert in interpretability, and all of the work that we've done has actually been in collaboration with her. So we've been incredibly lucky to get to work with her on this. If you're curious to learn more about the fairness side and some of the fairness interventions, so I'll actually give a shout out to give a tutorial yesterday together with Sam and Korea Joe on algorithmic fairness, why it's hard and why it's interesting. So this was basically 3.5 hours of content around algorithmic fairness. We'll make the recordings available and the slides available. And so I will refer you to that. And now I will pass it off to, I guess I'm happy to take a couple of questions and then we'll pass it off to Ruth, who will talk about some of the interpretability work. Yeah, if you have questions, feel free to come up to the mic.
You talked about revising this implementation of Coco. I have a question.
Yep.
In Rethinking, you come up with a new data set, which is not so well allocated in terms of social context and stuff like that. And we want to understand how biases are gender, race, or geography mitigate. Should we use some sort of like along with device or use a deep learning model? Use that as bias of that. So what's your take on a new data set and trying to come up with an analysis of what's the right one for that is not so well?
Yeah, that's a great question. So the question was, so in case folks didn't hear it, so the question was, so revise, I presented a result on Coco, but what happens when you have a new data set, in particular a new data set that has fewer annotations? So we tried to revise on a large set of different data sets. So essentially revise itself, right? So it'll try to get as much information out of a data set as possible. So if possible, it will use existing annotations. If not possible, it will run a bunch of pre-trained models. Yes, you are correct that these models may be biased. That is true. So are human annotators. So I think the bias in the annotations, that is always something you have to sort of be aware of and take into account. There's also a lot of work on sort of unsupervised bias discovery. In particular, Judy has actually done some work on this. So she has some work on kind of unsupervised analysis of data sets and bias discovery. So there's definitely some work on that. But ultimately, right, I think there's always sort of this trade-off between like how much can you do automatically versus how much do you get annotations, and there's also the question of like who's doing the annotations and how does that factor into the analysis again. Sort of, yeah. Yeah.
It requires, always requires human knowledge, records to them looking at the data.
Yeah, so it's a great question. So the question is, how do you discriminate whether it's a bias or a useful feature? So we try to give a lot of sort of answers to this in the tutorial yesterday. The short answer is a lot of the time you can think about bias from a harms framework, from the framework of sort of, are these predictions harmful to somebody or harmful in some way to some, and there's sort of definitions of what are the different types of harms and so on. So I think that's kind of how I think about bias and fairness questions versus sort of, you know, questions of spurious correlations more generally, or just questions of like, yeah, the model learned what it learned and did the best it could, and you know, even if it doesn't learn the right feature, okay, so but it still does well on the test. So that's sort of the distinction we make. Mm-hmm.
Okay, thank you for that great talk. I'm Shen from NYU, and I have a question regarding like you just show us like a lot of biased data set. And my question is that does biased data set always lead to a biased model, or in this case it will lead to, because we know that, for example, we see for example, the data set contains a lot of men playing like outdoor sports. Is that always true that the model will like learn on this data set will like also learn on men instead of learning how to classify or do jobs sometimes?
Yeah, so that's an excellent question. So does a biased data set always lead to a biased model? So the answer is no. The answer is definitely no, right? So a model will pick up on whatever cues sort of from the data set and not necessarily pick up on bias. So actually, let me go back here for a second. So this understanding bias propagation, I don't know if you can see my mouse, but the understanding bias propagation, so a lot of that literature is actually asking this exact question. And so the last work that I'm citing here by Dora Zhao and Angelina Wang and myself called Understanding Racial Bias in Image Captioning, I think published at ICCB last year. So we actually looked at kind of under what conditions does bias from image captions propagate into learned models. And it turns out that for some of the older image captioning models, they don't capture any kind of racial or gender bias because they're just not super descriptive. They say generic things and are pretty robust to any kind of bias in the data, whereas the newer models, right, the ones that are actually producing much more detailed descriptions and have much more capacity, they actually tend to be a little bit more biased.
Yeah, and like it's not true that is there any general something that more like there are like a general things
yeah, so I think the question is, are there general principles under which the model will capture biases? So I think the general principles are the model will capture the most visually discriminative cues, right? So that's the high level general principle, right? And as we've shown in the result with gender rates, so something like gender even in a data set like COCO rates, so those sort of features that are correlated with gender appear to be quite discriminative, quite robust, which suggests that it's likely that the model will be capturing those, and then by virtue of capturing those, that will be capturing some kind of correlations with gender. So yeah, that's the short answer. Yep, absolutely. Okay, last question, and then we'll move on to Ruth's talk. Mm-hmm.
Obviously, and do you think like that bias there will be a few samples that will contribute more for this bias, or there will be some continuous distribution of those data samples that joins that overall bias?
Right. So the question is, do I think there's sort of a few samples from the data set that are particularly kind of problematic, or it's the overall pattern in the data? Is that the question? Yeah, so that's a good question. I don't know. My guess is that this is task dependent and depends on what exactly you're training. Because I kind of could argue both sides of that, I think. For what it's worth, the tutorial yesterday was around taking 7 narratives and then arguing sort of both sides of each narrative. And I could imagine this being one of the narratives where we kind of discuss the nuances and the pros and cons. It wasn't, but it's sort of that kind of question. I think it would depend on the context. Yeah.
I was curious whether
yeah, so that's a very good point. So you can think of this in terms of influence functions and sort of think about influence functions and which help quantify kind of the effect of each training examples. Yeah, absolutely. That's a good point. All right, thanks so much, Ruth. I gotta give an intro. I'll do an intro. Okay. Sure. Okay. So it's my great pleasure to introduce Ruth Hung. So Ruth is, as I've mentioned, an expert in interpretability. Did her PhD at Oxford and is now on faculty at Princeton in computer science. I'm very, very, very happy to have Ruth as a colleague and collaborator, and she's done really excellent work in interpretability and is, as I mentioned, one of the world experts in this space. Okay.
All right, thanks Olga for that I think, over the top intro, and also thanks Foley for really organizing this wonderful talk. And like Olga mentioned, I'm currently faculty at Princeton, where I get the opportunity to collaborate with Olga and many of the other faculty there. And today I'll be talking about some of our work on interpretability with a particular focus on what have we done in the first decade, and where should we be looking as we enter the second decade of deep learning. If the Wi-Fi is working, you can grab the talk slides as well as all the papers that we'll be referencing at the QR code. So what do we mean when we say interpretability? Here we're talking about any work that focuses on explaining complex AI systems in a human interpretable way. In the past decade, we've been focused on explaining deep neural networks, as these networks are highly parameterized on the order of millions to billions, and now even trillions of parameters when we think about large models. And thus, these are really difficult to understand and characterize. Why would we need interpretability? There's a few different motivations for this type of work, and I'll just mention three. The first is a scientific curiosity to understand these complex models. This is similar to how neuroscientists study the human brain. And the second is to engender trust in AI systems. You can consider the scenario of AI-assisted medical diagnoses. A doctor may want explanations of how an AI system made a certain prediction in order to trust and use that system. And that may be particularly relevant as we consider different kinds of biases that may be in these systems. So we may not be able to trust each prediction equally. And the third is to learn from AI systems themselves. Bole hinted at this, and you can consider AlphaGo, which has now surpassed expert human ability in the ability to play the classic game of Go. And now human players are studying AlphaGo games to improve their own play. And we can imagine that explanations of AlphaGo decisions could really help facilitate and expedite that learning process. There's other types of considerations, such as policy considerations. In the EU, where I did my PhD, the General Data Protection Regulation from 2018 enumerated a right to an explanation from algorithmic decisions. So we're quite a far cry away from that, but this has been already enumerated as a thing that we really want to be able to provide to citizens. So given this variety of motivations, it naturally follows that explanations may look very different depending on the reason for the interpretability. And we'll discuss that along the way. So before looking forward to the next decade of exciting research directions, I'll give a very brief and incomplete retrospective of the first decade of deep learning and interpretability. And here, the years are just representing the years from the particular early works I'm presenting. I'm not trying to place time limits on anything. So in deep learning, there have been a number of exciting developments in the past decade. Starting off in 2012, when AlexNet and ImageNet together demonstrated the power of CNNs when given enough training to make much progress and kind of generate this new AI revolution. To work in generative modeling, first through GANs, and then more recently with diffusion models like DALL-E 2 and Imagine. And we've also seen more crosstalk between adjacent communities like multimodal self-supervised learning using audio for training signals, as well as transformers making large gains in NLP first and now vision. These are just a few of the exciting movements in our research communities, and ideally we hope that interpretability moves with our broader community as new frontiers are explored. So how do we do in this past decade? In interpretability in the past decade, there have been 2 or 3 main dominant research areas. The first has been focused on explaining why a model made a specific output prediction. And from this theme, attribution heat maps, which visualize where a model looks for evidence for its decision, arose and became the most researched area within interpretability. The second major focus has been on understanding the internal workings of deep neural networks. And here, researchers most actively developed various feature visualizations, which visualize what visual stimuli most activated individual channels or neurons in a network. Both of these approaches primarily explained and studied existing methods post hoc, meaning after that they've been trained. And the third and most recent development has been on developing models that build in an explanation as part of their decision-making process. And these are called interpretable by design models. Unfortunately, this doesn't map too well onto that timeline that I showed you on the previous slide. Whereas these 3 main research teams primarily focus on understanding and approximating supervised CNN classifiers, we really haven't done a great job covering the variety and breadth of work that's been done in the past decade. There have been a few notable exceptions like GAN paint, as well as transformer circuits that focus on understanding GANs and transformers respectively. But on average, we primarily focused on CNNs. So looking forward to the next direction, here's a few key directions I think will be crucial for the next decade. The first strand is to develop interpretability methods for diverse domains. We need to move beyond CNN classifiers and develop interpretability for the wide range of research that is happening and represented at this conference. And the second is to center humans throughout the development process. Specifically, when developing methods for engendering trust, we need to have real-world stakeholders at the table and understand their interpretability needs. Currently, most existing works aren't suitable to be used in the real-world settings. Also, in evaluation, we need to be critically measuring the human interpretability and usefulness of our methods. Finally, in deployment, we need to package our tools so that they can be easily used by the wider research and ML practitioner community. So in the rest of the talk, I'll be discussing 4 of our recent works that move along these directions and highlight some of the current challenges to developing these works with these goals in mind. And the first 2 are done in collaboration with Olga Rostkowski and her students. So first, I'll discuss our recent work 5 on evaluating the human interpretability of visual explanations. In this work, we moved from automated evaluations of interpretability towards more human-centered evaluations via human studies. And this project was led by Princeton PhD student Sunny S. Kim. So here we're primarily focused on explanations that answer the question, why did a model predict a specific output class? So we already mentioned attribution heat maps, but there's many more kinds of explanation form factors that tackle this problem. For instance, there's been a line of work on concept-based explanations that explain a model's prediction based on the presence or absence of interpretable attributes, such as the presence of black wings in this example. Another class of explanations explains a model's prediction based on how similar image patches in the input image are to learn prototype patches from the training set. Lastly, counterfactual explanations answer a slightly different question of why did a model predict one class over another? And ideally, we'd like an evaluation setup that allows us to compare and contrast the usefulness of the variety of these kinds of explanations. Another axis of variation is how the explanation is produced. So as I mentioned earlier, post-hoc interpretability methods like attribution heat maps, for the most part, explain a model after it's been trained. That is that the explanation is not part of the model's original design. In contrast, interpretable by design models are ones that are designed such that they produce and use an explanation as part of the model's decision-making process. And we similarly want to compare post-hoc and interpretability by design methods in our evaluation. So what's the state of evaluating these kinds of explanations? For the most part, current metrics focus on evaluating only one kind of explanations, namely post-hoc attribution heat maps, and most are about automated evaluation metrics. And I'll briefly mention 2 right now. So the first metric was to quantify a heat map's ability to explain a specific output class. So here we generated heat maps on the top row, explained a golden retriever prediction on the top, and on the bottom, a tiger cat prediction. And what's surprising about this figure is that most methods generate nearly identical heat maps for both classes. This suggests that the heat maps aren't actually explaining something specific about a model's prediction for an output class, but rather maybe something more general about, say, its image content. Similarly, the sanity checks paper by Adebayo et al. In NeurIPS 2018 showed that several attribution heat map methods weren't sensitive to a model's parameters. And in this experiment, the authors successfully randomized model weights from the end of a network all the way to the beginning and showed that for some heat map methods like guided backdrop, the visualizations didn't substantially change. So what you're seeing here on the rightmost side of this figure is when the model weights are completely randomized. And you can see for guided backdrop, you get nearly the same heat map as when the model weights were these pre-trained weights. This paper was really a wake-up call for our interpretability community, and it highlighted the need for critical evaluation. Before this, our community was arguably over-focused on looking at qualitative examples of beautiful heat maps, but rarely tested hypotheses of their actual usefulness and faithfulness for the types of model explanations that we desired. So as I mentioned before, most evaluations are were automatic and primarily focused on measuring the faithfulness of explanations, but there have been a few recent exciting works developing human evaluations for heat maps, and I'll just talk about one briefly. So in Wen et al. In NeurIPS 2021, the authors studied whether heat maps helped users identify when a prediction was correct. So given a sample image on the left and its predicted label on the top, participants were shown one of the three. A, they were shown a prediction confidence by the model. B, they were shown a single heat map explanation, so just one GradCam explanation. Or C, they were shown the three nearest neighbors for the predicted label. And on ImageNet, the three nearest neighbors, which was really just a baseline, outperformed the heat map method, suggesting that they weren't useful in detecting model failures. So kind of building on, especially the recent work on human studies for heat map evaluation, in our new work Hive, we have three main goals. The first was to enable this cross-method comparison, in contrast to prior works that primarily focused on evaluating heat maps. The second was to center humans in the evaluation process and measure if interpretability methods were actually useful to humans, in contrast to prior works that focused on automatic evaluation and really measuring the sensitivity of these heat maps for certain desiderata. And finally, we wanted to enable falsifiable hypothesis testing. This is in contrast to intuition-based reasoning that led our community astray in the first few years of this heat map development work, and that was kind of really revealed as a big problem in our community by the Sanity Checks paper. So our contributions were as follows. We present a novel human study that evaluates for diverse interpretable methods, and in particular, we're the first human study to one, evaluate interpretable by design and prototype methods, and two, to kind of compare these with heat map methods. Our study also quantifies the usefulness of explanations in distinguishing between correct and incorrect predictions, as well as how users would trade off between interpretability and accuracy in different scenarios. And finally, we open source our Hive studies to encourage reproducible research. So first, in our initial study, we evaluate four methods: GradCam, BagNet, ProtoPNet, and ProtoTree. And these techniques include both heat map and prototype-based explanations, as well as post-hoc techniques and interpretable by design methods. Our initial study included two tasks. The first agreement task measured how confident a participant was in a model's prediction, given an explanation for a single prediction. Our distinction class measured a participant's ability to distinguish which is the correct class, given several explanations for different classes. And for each study of a particular explanation, we recruited 50 participants through Amazon Mechanical Turk. As I explain these tasks in more depth, I'll also highlight a few of our key findings. Here's a condensed UI for our agreement task, which asks participants to rate their confidence in a model's prediction. For prototype-based explanations, we also include the similarity rating subtask in both the agreement and distinction tasks that ask participants to rate how similar an image patch here on the left is to a given prototype on the right. And this ensured that one, participants looked at and understood the prototype explanations, which on average were more complex than heat map explanations. And second, it allowed us to compare, are the computed prototype similarities, how well do they align to human notions of similarity? And it turned out that when we compared participants' ratings of prototype similarities, we found no significant correlation between their ratings and the model's computed similarity scores. Our study confirmed previous anecdotal observations made by prior work, but this is the first systematic study that really quantified and substantiated this claim. Our second finding is that the agreement task reveals the confirmation bias. When we analyzed participants' responses to the agreement task box in blue, we found that more than 50% responded that they were either fairly or somewhat confident that a prediction was correct. That is, they checked the top two answers. And this held true even when incorrect predictions were shown. So diving more into these graphs, here we're showing results on both Hub trained and ImageNet trained models. On the x-axis, we show results for our interpretability methods, and on our y-axis, we're reporting the percent of predictions deemed correct. That is the percent of respondents that checked one of the two answers with blue check marks. Here, the dotted line is 50%, which is our baseline for random guessing, and green circles denote results for correct predictions by the model, and orange triangles. Oh,
There's a thing that popped up on the screen.
Okay.
Navigate to that. Okay,
I'm gonna need your help because I can't see the screen. Hold on. Here. Oh, okay. Is it this way? Nope, this way. All right, I can.
Stop sharing.
Yes. Let me.
I'm sorry, it's like right in the middle of the screen.
Yes. Okay. Let's see. Yeah, we should have just turned it on. I don't know how to. Let me see if I can grab it.
Can you just make yourself co-host? Because then I bet I could do that.
Okay. The problem is it's up here. Oh, I think, okay, let's
Okay,
just,
you got it.
yes,
Okay, a little bit right, yeah.
great, thank you. Okay. All right. No. All right, so I was explaining the graph. 50% is our random, our baseline for random guessing. Green circles denote results for correct predictions by the model, and orange triangles show results for incorrect predictions. And here what we want is correct predictions to be as high as possible, as close to 100%. And we want our incorrect predictions, the orange triangles, to be as low as possible. And what's key here is that our orange triangles are above our 50% random chance baseline. What this suggests is that even though there is a gap between participants' confidence between correct and incorrect predictions, the incorrect predictions are still above our 50% random baseline, meaning that participants believe them to be correct more often than not. And this highlights how providing an explanation may erroneously convince a user that a model prediction is trustworthy. We argue that future work should really check whether the explanations encode such confirmation biases. Moving on to our distinction task, here's a condensed example UI of our task, which asks participants to select which class is correct based on explanations for 4 different output classes of the same input image. And when analyzing responses to the first question in blue, our third finding is that participants struggle to identify the correct class, especially for incorrect predictions. So again, diving deeper and looking at these graphs, the x-axis shows each method, and the y-axis reports the mean accuracy of participants in answering the question correctly, where here higher is better. The dotted line is at 25%, which is the baseline for randomly guessing one of the 4 choices. And red circles again denote correct predictions, while yellow triangles are for incorrect predictions. And you'll note that for prototype methods, there's no orange triangles or no incorrect predictions. This is because we chose to show only correct model predictions to reduce the study complexity. We found that as we were designing the study, the prototype-based explanations were really much more complex than the heat map ones, and participants struggled to complete the task within a reasonable time. So even with the simplification, the proto-PNET study was twice as long as that for heat map explanations. So recalling that 25% is our random baseline, we found that participants' accuracy for incorrect predictions is either around or barely above this baseline. And what that says is that these explanations aren't really helpful for aiding participants in distinguishing and understanding model failures. So here we're really showing that there's so much room for improvement, even for explanations of correctly predicted examples. And here the takeaway is that the distinction task results suggest that interpretability methods should improve their ability to identify and explain model errors. So recall that our third goal was to enable this falsifiable hypothesis testing. And our key findings are an example of just that, where we test and either validate or reject hypotheses about explanations, such as our first finding was testing the hypothesis, are prototype similarities, do prototype similarities match human notions of similarity, and it rejected that hypothesis. At the end of our studies, we asked our participants a more subjective question, and we asked them to specify on a sliding scale how much more accuracy would they require a baseline model to have over a model with explanations. Here we asked participants to answer this question for 3 settings. First, for low risk settings, such as for educational uses. Second, for medium risk settings like biodiversity monitoring. And third, for high risk settings, such as veterinarian science. Here, the x-axis shows the risk setting, and the y-axis reports the mean required accuracy gain a baseline model needed to have over a model with explanations in order for participants to prefer that baseline model. So explaining the high-risk setting bar on the right, participants required a baseline model to have almost 11% higher accuracy than a model with explanations. And here, what we wanted to note is that participants increasingly desired stronger performance for a baseline model in order to prefer over a model with explanations, especially as the risk of these different scenarios increased. This suggests that humans prefer explanations, particularly in high-risk settings, to the point of being willing to trade off more accuracy further. That said, the results from our prior two tasks suggest that the usefulness of current explanations is limited in real-world AI human assisted scenarios, and we really need to close this gap that we highlighted in our studies. So zooming out, we identified a few challenges for future human evaluation work. The first is an obvious skills cost in human studies. That is, we need really strong web development skills, and it's really a testament to our lead student authors that really actualized the Hive studies and made them kind of the amazing UIs that you saw. The second is, again, an obvious financial cost in being able to budget for human experiments. And the third, I think, is more subtle, that there's a time cost that arguably is different and possibly longer compared to more traditional GPU-oriented computational experiments. And this is for human study design and iteration. And it's not just for iterating on the UI, but it also includes things like ensuring that the tasks are feasible for participants, getting IRB approval, and incorporating quality control measures in your study. So despite all these costs, we still think that human evaluation is crucial to interpretability because the whole point of interpretability is that we want these methods to be useful for humans. So a main key takeaway is that as a research community, we need to be investing in and rewarding human evaluation studies, just like we do for data set development, which has been crucial for progress in our field. And similar to how we budget for GPUs and cloud compute, we need to be budgeting for human evaluation in these different ways. So the second work I'll be discussing is our work on Allude, which focuses on generating interpretable explanations via decomposition into labeled and unlabeled features. Here we move from concept-based explanations that use only labeled attributes to explaining model decisions with both labeled attributes and unlabeled features. And this project was led by Princeton PhD student Vikram V. Ramaswamy. So for background, concept-based explanations aim to answer the question, why did a model predict a certain class? They do this by explaining a prediction via the presence or absence of labeled attributes. For instance, a concept-based explanation may explain that this model predicts sheepdog when fur and paw are in the image, but when trees are not. And the main benefit to this approach is that label concepts are interpretable to humans. It's easy for us to reason about the presence of fur and paw in tree. One great example of concept-based explanations is concept bottleneck model. This is an interpretable by design model, which predicts the presence or absence of attributes and learns to weigh the importance of each attribute for a given output class. It then linearly combines everything to form its output prediction. However, there's a few problems with using these fractional values that it outputs. First, it can be really hard for humans to reason. What does it mean when the logic for fur is 9.2? Second, and this is probably more important for our discussion, they can encode hidden information. For instance, when the authors passed their presence and absence vector through a sigmoid function, effectively binarizing these fractional values, the performance dropped for the downstream tasks dropped significantly, which suggests that the fractional values are encoding some hidden information that wasn't related to the attributes that they were supposed to be explaining. So building off of the concept bottleneck model, our latest work, Allude, which stands for explanation via labeled and unlabeled decomposition of features, differs in a few key ways. The first is we aim to approximate the behavior of a model after it's been trained. So this is a post hoc technique instead of training an interpretable by design model from scratch. And the second is that we aim to do this by explaining the model's behavior as a decomposition of labeled and unlabeled features. And so recall that this is our goal. So what we first do is we learn to make predictions by linearly combining ground truth attributes for an input image. And note that this indicator vector is binary, it's not fractional. So it solves that first problem we mentioned. After we've learned to explain as much of the model as possible via these labeled attributes, we then learn the remaining unlabeled features as a low rank space. And then we can analyze what's learnable via attributes only versus what can only be represented using our feature space. So let's focus about what we can learn using attributes only. Here we show results for when we're trying to explain 3 different scene prediction tasks of increasing complexity. And we're quantifying how well the labeled attributes explain the original model. That's how well they match the original model's output prediction. We find that as the task complexity increases, so when we go from a 2-way classifier to a 16-way classifier to a 365-way classifier, the amount of labeled attributes that can be explained by the original model's predictions decreases. So in our simple classifier of indoor versus outdoor scenes, we could explain the original model with around 95% of our predictions, but this drops to below 30% when we're looking at a fine-grained scene classifier. And sorry for the kind of cutoffs. If you go to my website, you can see the PDFs of the slides, which should have it formatted correctly. What this highlights is a problem with using fractional values instead of binary attributes. So I would argue that kind of some previous works that only use attributes, we didn't really realize that as the task complexity increased, our attributes become quite limited in their ability to explain a classic CNN model. We can kind of dive in, and here we're analyzing our 16-way coarse scene classifier and break down performance for each output label. So here we're showing the true positivity rate for predicting each label as the original model did. And while we know that some scene groups do quite well, for instance, home and hotel can almost entirely be explained by attributes alone, about half a dozen scene groups at the bottom can't be explained at all using attributes. This suggests that perhaps the attributes being used are more relevant for some groups and not others. So then we really want to move towards understanding our learned feature space. So here on the left, what I'm showing is in each row, we show a few maximally or minimally activating images for directions from our low rank feature space. Here, this is a rank 4 feature space for predicting our coarse grain scene groups. And what you notice is that these are pretty semantically coherent. So the top row seems to encapsulate this bowling alleys, whereas the third row seems to capture outdoor sports and fields. And when we pull up the table from before, we notice that some of the directions from our low rank feature space actually map on quite well to the scene groups that couldn't be explained using attributes alone. For instance, bowling alley is an indoor sports and leisure scene, and both indoor sports as well as outdoor fields were not explained by attributes alone. What this suggests is that understanding this feature space is key for us understanding what still remains to be explained by concept-based methods. And our method can be viewed as a recursive decomposition, where we can imagine discovering new attributes to include from our low-rank feature space and slowly work towards reducing this remainder that can't be explained using attributes alone. So zooming out, we realized a few challenges for developing concept-based methods. The first is that attribute-only approaches are incomplete, and we need to recognize that whenever we're developing this class of methods. The second is we need to develop some more methods that explain this remainder part. There's been some amazing work on this, but kind of from our exploration, we invite much more work towards the space. And third, we want to ensure that the concept-based explanations are actually truly human interpretable. So what we notice in our work is that some explanations use over 100 concepts, and we're not confident that humans can reason about that many concepts at once. This ties into our first work, Hive, where we want to critically evaluate the interpretability and usefulness of different kinds of explanation methods. So one takeaway from all of this is that we need to be realistic about the benefits and limitations of interpretability methods and work towards meaningfully addressing those limitations, not just for concept-based methods, but more broadly. I would say that if we realized this early on in our heat map development, we could have kind of saved a lot of time in that research progression. The third work I'll discuss is our NeurIPS 2020 work on quantifying the learnability and describability of visual concepts emerging in representation learning. And in this work, we move from focusing on understanding supervised models to understanding self-supervised models. This work was led by Oxford postdoc Dr. Eero Leena. So recall that in supervised learnings, we're learning to predict our labels Y from inputs X. And in self-supervised learning, we don't have labels. We can only learn from our inputs, which are typically images or videos in computer vision. So what can we learn with just images? Let's consider the scenario where you can imagine that you have some groups of images where we present here as rows, where each group defines a visual concept. Here, humans can easily learn concepts from examples and then decide whether new images are instances of these concepts without necessarily needing to name them. For instance, we all can probably match these new query images to the groups that they most likely belong to. In the past decade, self-supervised algorithms have reached and even surpassed supervised pre-training on ImageNet on downstream tasks. However, most interpretable works have focused on supervised learning, and we argue that we need to develop a deeper understanding of the representations learned by these self-supervised paradigms. In this work, we asked the question, to what extent are methods able to discover human interpretable concepts? So currently there's two main trends for obtaining these kinds of groupings. The first is to jointly learn representations in pseudo labels, and these directly yield a set of self-discovered clusters. And the second is to apply a clustering algorithm like k-means offline on top of the learned representation. So we propose two measures based on human judgments. The first we call learnability. Here we're checking whether a visual grouping is interpretable and coherent. And we measure this by testing the ability of humans to discriminate new instances of a group from negative ones in a forced binary choice setting. The ground truth is determined by the self-supervised method that's being evaluated. And here, most of us can probably guess that the correct answer is A. This is the image that belongs to the cluster of examples that were shown on the left. Furthermore, a human could probably even describe this concept grouping succinctly. I might describe this as a white animal in snow cluster. However, being able to learn patterns from images doesn't necessarily mean we can always find the words to accurately describe them. For this reason, we introduced another measure, which we call describability. Here, instead of showing a visual set as a reference, we instead summarize the group with a short description in natural language. The reasoning is that if humans can accurately predict which image fits the description, then the group is not only interpretable, but also describable. In this example, you can probably guess that the correct answer is B. Oops, sorry. That the correct answer is B. This matches the description. It's supposed to say dessert with chocolate sauce. Here we conduct experiments with descriptions provided manually by humans, but we also answer the question, to what extent can these groups be automatically described by evaluating a group level capturing system? So we conduct our evaluation and our studies on Amazon Mechanical Turk using clusters from two recent methods, Sella and Moko, and here we're measuring the human accuracy on the two tasks. So in this graph, each point represents a different cluster, where the orange points represent Moko clusters and the blue points represent Sella clusters. On the x-axis, we plot the ImageNet cluster purity for a cluster, and this metric roughly measures how correlated a cluster's content is to a single ImageNet label. For instance, a cluster with a purity of 1 exclusively contains images from a single ImageNet class. On the y-axis, we plot the mean participant accuracy on our learnability class. So now this highlighted orange dot represents a Moko cluster with low ImageNet purity. That is, it doesn't correlate well with any particular ImageNet label, but it achieves nearly 100% in our learnability task, suggesting that it encodes a very semantically coherent concept despite not being correlated with an ImageNet label. And when we look at a similar graph for our describability task, we also find that clusters can be described automatically almost as well as they can be learned from visual examples. And when we get to a purity of around 0.5, we get almost 90% plus accuracy on our tasks. So we can look at a few qualitative examples. And here we find that a large portion of our clusters are in fact human interpretable and semantically meaningful, even those that don't correspond to ImageNet labels. That is, that they have low ImageNet purity. Here's a few such clusters where we could probably give labels to these. For instance, the left one I might say is newborn babies lying on a bed or a crib. In the middle, I might say that these are all some sort of reptile and snake-like creature on a human hand. And when we run our evaluation metrics, we find that these are in fact very easy to interpret and describe. So I just want to give a shout out to some follow-up work which uses concept pseudo labels to measure the semantic coherence of self-supervised clusters. So zooming out, we recognize a few challenges for developing interpretability for new frontiers in the field. First, we need to understand the unique interpretability needs within a particular research area and develop specifically for that. It's not as simple as applying existing methods to a new domain. For instance, most prior work on understanding CNN classifiers often explained a particular output class, and that setup just didn't hold up for most self-supervised paradigms. Second, especially in newly developed areas, we ran into a problem early on in the first wave of self-supervised learning, where the lack of access to open source implementations, or even a lack to standardized implementations, made it really difficult to reproduce these models and then subsequently develop interpreting methods for them. So I believe David Bao mentioned this in his talk yesterday in the AI content creation workshop. When we're looking forward to today's state-of-the-art large models, they have legitimate safety reasons for restricting access. But we argue that we need to consider how we can balance these safety concerns with a more open research style that also invites further accountability in the field. So one key takeaway from this is that we need larger collaboration and buy-in from the wider community, particularly those working at these new frontiers, in order to develop interpretability for these domains. So the last work I'll discuss is some of our work on interactive similarity overlays. And in this project, we move away from static visualizations to using interactive ones. So current interpretability tools typically render static visualizations, where on the top row, I'm showing you different methods for visualizing attribution heat maps, where a model is looking to make a decision. In the bottom row, this is highlighting different feature visualization techniques that describe what kind of visual features a network neuron is highly activated by. But we want to imagine, what if interpretability tools were interactive and leverage the full expressive power of modern web technologies? While there are some really amazing interactive visualizations, they more often than not tend to be well-polished demos that aren't easily extendable to new models. So we're particularly interested in creating these lightweight modular visualizations that any researcher can just drop in to their workflow with a few lines of code. So why do we want interactive visualizations? We argue that this is more human-centric. This allows humans to explore a model similar to how a doctor uses their stethoscope to easily examine different body parts quickly. We also argue that it's more digestible for a human, and the ability to represent content in an interactive visualization is easier than representing it using the equivalent information via a stack of static visualizations. So similar to the stethoscope example, we want to explore different hypotheses about a model, such as how do different layers in a network compare to one another, or what about different image regions? So our first visualization is interactive similarity overlays. Here, as we hover over an image, we dynamically render an overlay that shows how similar other image patches are to the current image patch highlighted in yellow. Lighter patches are more similar, while darker patches are less similar to the current image patch. Diving a little bit into the details, this is a very simple method. So if we consider a CNN and we cut it in the middle, the first part is going to produce an intermediate output for image classification models. This would be a 3D volume, and we can interpret this as spatial activations. What I mean by that is that every patch in an image corresponds to a cell in the activation volume that is a vector of activations, where each dimension corresponds to a channel in that layer. So after we compute the activation vectors at every spatial location, we then visualize the similarity or distances between activations at different spatial locations. And that's what we're visualizing. Lighter patches are more similar to the current patch, darker patches are less similar. And here we're using cosine similarity as our similarity function. So you can actually play around with the interactive article here. It's also on our website. I was going to do a live demo, but because of how hard live things are, particularly in hybrid settings, I'm just going to show you a few videos. So this is our splash image. Here we're able to compare image patches across different images. So note here that the current image patch in yellow is being compared across all other image patches in these 6 images. And we notice a few interesting findings. First, we notice that when we hover over animal features, such as the eyes or dog head, we notice that the corresponding features are highlighted in other animals. And second, when we start hovering over background regions, we notice that other image backgrounds are also highlighted, despite them being different colors. And this suggests that backgrounds, regardless of colors, kind of map to the same activation representation. We can also use our visualization to explore how different layers represent image patches. So in this example, we show overlays for activations after 3 different network layers. These are early, mid, and late layers in the Google net network, and we synchronize the highlighted image patch. So note here, and in each image, the highlighted patch is being compared only to the other patches in the same image. So now when we start hovering around, we notice a few things. For instance, on the left image, we notice that when we hover over low-level details, we kind of get these oriented edges. For instance, when I hover over the dog's head, I kind of get all these other 45-degree angled edges. This is in contrast to when I hover over later layers, I capture much more semantic concepts like the head of the dog or its torso. Finally, we can compare and we can combine our visualization with other techniques. So here what we're doing is we're showing a line plot on the bottom right-hand corner that plots the similarity scores of the highlighted image patch and its corresponding rotated patch in the other images. So specifically, when I'm hovering over this dog's nose, what's being plotted in the line graph is the similarity score with all the other dog noses in the rotated images. But combining this technique, we kind of combine a qualitative visualization with a quantitative plot that really amplifies what we can discover. For instance, as we start hovering around, we notice that when we hover over some of the animal features, these tend to be oriented and much more rotationally sensitive. So we see that the similarity drops. Whereas when we start going towards the background, we see that the similarity scores stay pretty high. And finally, when we start going to the edge, we notice this boundary effect where we get this oscillating pattern, and this is because of zero padding. So you can play around with that yourselves, and I just want to highlight that it's really easy to use our visualization. This works with both PyTorch and TensorFlow, and you can start using it as little as 10 lines of code. So we also have a new work that you can find demos for. This is in contrast to our similarity overlays, where we could only really compare activations of several hand-picked images. And in our latest work, Interactive Visualization Feature Search, we implement a reverse image search of sorts that allows users to select a free-form region in an image and then searches for nearest neighbors in activation space of a specific model and layer. So when I'm kind of highlighting the right side of this building at Princeton, I'm able to return the nearest neighbors from ImageNet are actually these arches from bridges. And we provide Colab notebooks to play around with our tool on our website. This project was led by Devin Urick, a Princeton undergrad student, and came out of some discussions with David Bao, another interpretability researcher. So zooming out, we noticed that there are a number of challenges for developing more interactive visualizations. Like human studies, there's a skills cost in web development skills. But thankfully, there's been a number of new platforms that I just discovered a few months ago, actually, that make it easier to make interactive visualizations and demos using only or mostly Python, and I'm really excited for this. Second, there's a potential for interactive visualizations to be misused as they're qualitative visualizations, just like the heat maps were. And while visualizations like these can be useful for developing intuition, we want to be clear that any hypotheses need to be tested with quantitative experiments. Third, we found that developing high-quality software tooling for research, not just interactive visualizations, aren't often rewarded. And I think this is a major bottleneck, that there's been some amazing interpretability work, but it actually takes a non-negligible amount of time to kind of get it working in a novel setting. And I think this is the reason why we haven't seen interpretability more widely adopted in our research community. Fourthly, in a similar vein, there have been really sparse publishing venues for interactive biz work. Distill was an online journal that had these amazing interactive articles, but unfortunately they went on hiatus about a year ago. But I think recently I've seen that the CVPR demo track allows for works for model inspection and visualization, so this may become a prominent venue for this line of work. Finally, we noticed that there's a lack of crosstalk between research communities. Specifically, there's been some great work on interpretability tools developed within the HCI, or human-computer interaction community, but we're often developing those tools independently in computer vision and HCI. So one of the main takeaways is that the relevant research communities need to collectively invest in and reward software tooling for research, particularly these interactive tools. So in summary, these were the main takeaways. First, we want to value human studies like we do data set development. Second, we need to be realistic and even critical about the benefits and limitations of our methods. Third, we want much larger buy-in and collaboration from the wider research community. And finally, we want to value software tooling for research, particularly interactive tools. So at the beginning of my talk, I described kind of these main key directions I think are going to be important for the next decade in interpretability. In addition to advancing interpretability to these new frontiers of deep learning, which I also want to give a shout out that there's been some really awesome work at ICML 2020. There was a workshop on extending explainable AI beyond the self-supervised domain. There's also some follow-up, a book that kind of collected some of the works that are on this new frontier. And this second part of centering humans throughout the development process, I think is really exciting for this next decade. So my hope is that in 10 years, we'll have methods that are demonstrably useful to a variety of humans. From ML researchers and practitioners who use interactive viz tools regularly, just like they use TensorBoard, to doctors using explanations to decide when to use or override an AI system in healthcare, to maybe a novice bird watcher who uses explanations for a bird prediction model to improve their own ability to recognize birds. So in conclusion, we started off with a retrospective of the first decade in deep learning and interpretability, and we're really excited to see what's going to happen in this next decade. In particular, we want to encourage those of you who are new, maybe you're here at CVPR for the first time, we find it's always useful to have more diverse minds working in this space. So we're really excited to see what all of us collectively come up with together. Finally, none of this work would be possible without my amazing collaborators and funders, and we're hiring. So if you're interested in working on interpretability and explainable AI and fairness, Olga and I are hiring postdocs, and we'd love to chat more.
Thank you very much for the workshop. I'm also interested in explainable AI, and I actually kind of confused them a long time ago. When we talk about interpretability, we always talk about explain the black box in the network. Or if you have like interpretable models from innovative, like interpretable by design. So I kind of want to know what do you think about the relationship in those two branches and development in the future?
So the question from the audience was, there's some works on explaining models post-hoc after they've been trained, and another line of work on interpretable by design, and how do we kind of weigh these two? I think it's realistic. I think right now where interpretable by design models are is that there is this trade-off between interpretability and accuracy in computer vision. Rich Karuna gave a really great talk earlier today at the XAI workshop, where that trade-off no longer exists for tabular data. So that would be really exciting if in the future we don't have to trade off between accuracy and interpretability, but right now in computer vision we do. So I think that's why it's still valuable to have these post hoc explanations, because I think realistically, most of the community is not going to move towards interpretable by design models. That said, I think that there is potential that as we kind of iterate more on this, that we can close that trade-off and that gap, and that interpretable by design models can become more promising and realistic for deployment. So I think that's a really good question.
Yeah, thanks, Dr. Pong. So that concludes today's lecture. So thank you for attending. I hope you enjoy your rest of days at CVPR. Thank you.